Good evening, and welcome to The Sleepy Scientist. Tonight we are settling into the quiet world of trees, those towering companions that stand so still we often forget they are alive, listening, and in their own slow way, speaking. This video will take us into that secret kingdom, exploring how trees live, communicate, and thrive together. Before we begin, I would love to know, where in the world are you listening from tonight? It's always fascinating to see the little forest of viewers scattered across the globe. If you find these calm journeys helpful, a gentle tap on the like button and a kind subscribe would mean a lot. To those already subscribed, thank you sincerely. It is your support that keeps these quiet explorations growing, and if you'd like to be sure you don't miss the next wander through science, please consider clicking the notifications bell. Now, I hope this video isn't so interesting that it keeps you wide awake, but if it does, at least you'll drift into tomorrow with a pocket full of tree secrets to share. After all, knowledge can make fine dream fuel too. So how exactly do trees talk to one another? And what kind of messages could be passing through the soil beneath your feet right now? To speak of talking trees, we first need to set aside our usual sense of speed. Human conversations unfold in seconds, with quick words, gestures, and glances. Trees, however, live on a slower clock. Their signals are drawn out over minutes, days, even seasons. Yet despite that difference, they communicate all the same, using chemical scents, subtle pulses of water and electricity, and vast underground fungal webs that function almost like nature's own internet. For a tree, communication is never about idle chatter. It is about survival. To live, it must capture sunlight, draw up water, and balance its budget of sugars, nutrients, and energy. These are the essentials, and communication helps manage them, whether that means warning a neighbour of approaching danger or calling on fungal partners in the soil for a needed supply of phosphorus. This video will guide us through those hidden channels of exchange. We will wander the scented trails of airborne signals drifting from leaf to leaf, follow faint electrical flickers that race through a trunk and dive beneath the forest floor into the fine threads of mycorrhizal fungi that connect roots like cables. Along the way, we'll see how cooperation and rivalry weave together in a woodland, how families of trees recognize one another, and how ancient giants hold entire communities in balance. The central idea is simple, though quietly astonishing. Forests are not collections of lonely individuals. They are neighborhoods. A forest is a web of messages and responses, with each tree bound to others in ways both subtle and profound. In their slow exchanges lies not only the story of survival, but also a lesson for us, a reminder that life flourishes through connection, even when it is nearly invisible. Tonight, then, we will listen to the conversations of the trees. They may not use voices, but they do speak. And once you know how to listen, the silence of the forest is never quite silent again. When people first hear the phrase trees talking, it can sound like the start of a fairy tale. One might picture oaks with deep voices, pines whispering in the wind, or ancient willows giving cryptic advice. It is a comforting image, but the reality, while different, is no less wondrous. Trees do not talk in words or sentences, yet they do send and receive messages. To understand how, we first have to clear up what talking means in the context of plants. In everyday life, talking usually implies language, symbols strung together with intention. Human language carries meaning because someone meant to send a message, and someone else understood it. In forests, however, things work differently. When a tree releases a chemical or pulses an electrical signal through its tissues, it does not do so with the conscious thought of warning the neighbour. Instead, it is an evolved response shaped over millions of years, a signal that helps a tree survive and sometimes helps its neighbours survive too gets passed along in the great experiment of evolution. This difference matters. It is tempting to imagine a forest as a society of conscious beings, gossiping about caterpillars or whispering about drought. But in science, signalling is not the same as language. A signal is simply a change, something measurable that carries information. It could be a burst of scent, a ripple of water pressure, or a shift in hormone levels. The tree that generates it is not making a deliberate choice in the way you or I decide to speak. Instead, the signal exists because it once made survival more likely. Over time, that survival advantage became part of the tree's biology. Even so, calling it talk is not entirely wrong. Talking is really just exchanging information, and that is exactly what trees do. They are sending and receiving cues, shaping their lives around what they perceive in their environment. The main difference is speed. While you can fire off a text message in a few seconds, a tree's equivalent might take hours or even days to unfold. Their conversations are written in slow motion. Some signals move surprisingly quickly. Electrical impulses, similar in a loose way to those in our own nervous systems, can spread through plant tissue in fractions of a second. When a caterpillar takes a bite, tiny voltage changes ripple through the leaf and down the stem almost instantly. Hydraulic signals, shifts in water pressure, can also move rapidly when roots sense sudden dryness. Yet many tree messages unfold at a pace that feels glacial to us. The opening of buds in spring, the timing of flowering, or the gradual yellowing of leaves in autumn, all of these are signals too. They tell neighboring plants when it's safe to grow, when it is time to release pollen, or when the growing season has come to an end. Such messages take not seconds but weeks and months. The variety of timescales is part of the magic. Imagine a forest orchestra where some instruments play in high-speed bursts, others drone on in steady tones, and still others hold notes so long they span entire seasons. Together they create a layered symphony of information, and the trees, along with countless other organisms, are attuned to this performance. Why do trees send signals at all? Survival is the simple answer. A tree is rooted in one place, unable to run from fire, pests, or drought. Its best chance is to anticipate challenges and adjust. Signals help it do this. They allow a tree to close its stomata when water is scarce, to release protective chemicals when insects attack, or to sync its flowering with its neighbors so that pollination succeeds. Signals are not luxuries, they are life-saving strategies. Consider the case of a young sapling growing in the shade of taller trees. It receives less light, but it is not helpless. By detecting changes in the color and angle of light filtering through the canopy, the sapling reads signals that guide its growth. It might grow taller more quickly, lean toward a gap, or delay leaf expansion until conditions improve. None of this is planned in a conscious sense, but it is nonetheless a kind of decision-making, with signals providing the information. Of course, with any discussion of talking trees, there is a risk of slipping into myth. Books and documentaries sometimes describe forests as if they were intentional communities, with wise old trees deliberately nurturing their offspring or sacrificing for the greater good. While those stories capture our imagination, the science is subtler. Trees do not make choices with awareness the way humans do. Their decisions are biochemical cascades, shaped by the long hand of natural selection. That does not make the reality less impressive. In some ways, it makes it more so. Without brains or nervous systems, trees have evolved a toolkit of signaling methods that let them coordinate with one another, fend off enemies, and thrive in ecosystems full of challenges. They remind us that communication in nature does not need language to be effective. It is also worth noting that not all signals are cooperative. Some are competitive, even hostile. When certain trees release chemicals into the soil that inhibit the growth of rivals, they are sending a message of exclusion. This patch of ground is mine, the chemicals say, though not in words. Signaling can be about sharing, but it can also be about staking territory. What unites all these signals, fast or slow, friendly or competitive, is that they make survival more likely. The forest is a place where danger can strike without warning. Insects arrive in swarms, fires sweep through, or drought lingers for years. A tree that can sense trouble, adjust quickly, and even influence its neighbors has an edge. Over thousands of generations, those edges have shaped the very fabric of forests. So when you next walk through a woodland, it may look still and silent, but that impression is deceiving. Beneath the quiet, messages are moving constantly. Some are flashing like lightning through living tissue, others drifting invisibly on the air, and still others playing out over the span of entire seasons. To human eyes and ears, the forest is calm. To a tree, it is alive with signals. The idea of trees talking, then, is not fantasy, but a gentle reframing. We can call it communication without language, conversation without consciousness. It is not the chatter of friends around a campfire, but the slow, steady exchange of information written in chemistry, electricity, and growth itself. And perhaps that is the greater wonder, that even without voices, trees have found ways to speak. Every tree is a living skyscraper of wood, leaves, and roots, but beneath that towering calm lies an economy as intricate as any human city. Instead of coins or banknotes, the currency is sugar, tiny molecules of glucose manufactured in the leaves under sunlight. A tree's economy begins with photosynthesis, that quiet miracle in which carbon dioxide from the air and water, drawn from the roots, are woven into energy-rich sugars. Each beam of sunlight caught by a leaf is a paycheck, and the tree spends its life balancing the books. Like all budgets, there are expenses. Respiration is the unavoidable cost of keeping cells alive. Just as a household pays for heating, water, and food, a tree must pay in sugar to fuel the basic functions of living. Running enzymes, repairing tissues, and transporting materials. Even while appearing silent and still, a tree is constantly spending energy to maintain itself. Roots keep growing, leaves regulate water loss, and protective compounds are produced. In winter or drought, when income falls, the bills do not stop. The tree has to dip into savings, and if reserves run too low, death can arrive quietly. Managing this flow of income and expense requires a transport system, and that is where the phloem comes in. Phloem tissue is the banking network of the plant world. Sugars created in the leaves, called sources, are loaded into the phloem and moved to sinks, the tissues that need them. Growing root tips, developing buds, swelling fruits, and even shaded leaves all act as sinks. This source-sink dynamic is constantly shifting. In spring, roots and buds demand the lion's share. In summer, swelling fruit becomes a strong sink. In autumn, storage tissues, often deep in the trunk or roots, take priority as the tree prepares for dormancy. The flow is not random. It is regulated by pressure and concentration gradients, a process sometimes described as pressure flow. Sugars move from areas of high concentration to lower concentration, carried by streams of water drawn through the phloem like syrup in a system of pipes. In effect, the tree pushes and pulls its resources to where they are most needed. Remarkably, this allows for a level of redistribution that looks a little like generosity. A sunny branch may produce more sugar than it needs, and those extras can be shipped to shaded branches or even to neighboring seedlings connected through root grafts or fungal partners. It is not generosity in the human sense. It is still biology, but in practice it can make the difference between life and death for a young plant waiting for a gap in the canopy. Trees also understand in their biochemical way the value of saving. Starches and sugars can be tucked away in storage tissues, creating a kind of carbon bank account. These reserves allow survival through the lean months of winter, or during prolonged droughts when photosynthesis slows or stops. Some of the most ancient trees owe their longevity to prudent budgeting, keeping deep reserves that can be mobilized after storms, fires, or insect attacks. In this way, a tree's memory of past seasons is etched not only in its rings, but also in its hidden storehouses of carbon. But every economy faces trade-offs. A tree cannot do everything at once. Growth, defense, and reproduction are competing demands on its sugar supply. When conditions are favorable, a tree may allocate more to rapid growth, pushing its branches higher toward the sun or thickening its trunk to outlast storms. Yet if herbivores begin chewing at its leaves, or pathogens creep into its bark, resources must be diverted to defense. Chemical weapons such as tannins, resins, and alkaloids are expensive to produce, and every drop of sap that goes into them is a drop not available for new leaves or roots. Reproduction is another costly investment. Producing flowers, fruits, and seeds demands enormous amounts of sugar. In mast years, when a species synchronizes to produce a bumper crop of seeds, trees may exhaust their reserves to flood the forest with offspring. The payoff is survival through numbers, ensuring that at least some seeds escape predators and germinate. But the following year, trees often reduce growth or produce very few seeds, recovering their balance sheets. It is an economic boom followed by necessary austerity. These trade-offs are not trivial. They shape the very structure of forests. A fast-growing pioneer tree invests heavily in rapid vertical expansion, racing to the light. It burns through resources with little thought of tomorrow, like a startup company chasing growth at all costs. In contrast, a long-lived oak or cedar plays the patient investor, allocating resources cautiously, storing generously, and defending strongly against pests. These strategies exist on a spectrum, but together they create the diversity of forms and lifespans that we see across woodlands. What makes this economy fascinating is how it adjusts to stress. During droughts, stomata close to conserve water, but this also slows photosynthesis. Income drops, while the costs of survival rise. The tree has to dip into its reserves, deciding, if we can use that word loosely, whether to protect current tissues or sacrifice some in order to save the whole. Leaves may be shed early, roots allowed to wither, or growth rings reduced to a fraction of their normal width. Each choice reflects the balancing of the budget, with survival as the ultimate goal. Even communication between trees fits into this economy. When a tree signals distress through chemicals or root networks, it is spending energy to warn its neighbors. The neighbors, in turn, may prime their defenses, increasing their own expenses before the threat even arrives. It seems counterintuitive, but the shared cost can be worthwhile if it helps stabilize the wider community. After all, a forest is not just individual trees, but a network where the health of neighbors often determines one's own fate. From this perspective, the stillness of a forest takes on a new light. Beneath the calm, each tree is running a sophisticated budget, managing flows of sugar with as much care as any accountant. Some days bring surplus, others deficit, but the balance sheet must always stay in the black. There are savings for emergencies, investments in defense, and big spending splurges on reproduction. It is not just biology, it is economy in green. So the next time you walk beneath a canopy, imagine the silent transactions humming through phloem and storage tissues. Picture sugars flowing like invisible coins from branch to root, from leaf to seed. Think of trees as bankers and spenders, risk takers and savers, all working with the same limited currency of carbon. And consider this. If an entire forest is engaged in such quiet economics, then perhaps the richest marketplace on Earth is not the bustling city, but but the shaded woodland, where every beam of sunlight is transformed into wealth, and every leaf is a ledger keeping track of life itself. Water is the quiet lifeblood of every tree. Without it, no sugar can be made, no leaf can expand, no root can grow. Yet the way trees move water is nothing short of astonishing. They do it without pumps, without moving parts, and without a single engine. Instead, they rely on physics, harnessing the pull of evaporation, the stickiness of water molecules, and the structure of their tissues to haul thousands of liters upward against gravity. If you have ever wondered how a 100-meter-tall redwood manages to quench its thirst, the answer lies in the strange elegance of the Zealand Highway. At the heart of this story is cohesion-tension theory. Water molecules are a bit like an overly affectionate crowd. They cling to each other thanks to hydrogen bonds. When one molecule evaporates from the surface of a leaf, it tugs on its neighbour, which tugs on the next, and so on, all the way down to the roots. Imagine a chain of people passing along a rope. When the one at the top pulls, the whole chain shifts. In a tree, that rope is a column of water running through the xylem, the long tubes that stretch from root tips to canopy. The pull of evaporation, known as transpiration, creates a negative pressure at the top, and cohesion allows that pull to transmit down the entire length of the column. Against intuition, water does not get pushed up the tree but sucked upward, drawn by the thirst of the atmosphere. This system is beautifully efficient but also precarious. Columns of water under tension are not invincible. Under high demand or drought stress, air bubbles can form inside the xylem, a process called cavitation. When this happens, the continuous chain of water is broken, like a snapped link in the rope. The bubble expands, blocking flow, and the conduit becomes useless. If too many embolisms, as these blockages are called, spread through the xylem, a tree can wither even while water is still present in the soil. It is like having a plumbing system full of airlocks. No matter how much water you pour in, nothing reaches the tap. Trees are not helpless in the face of this problem. Some can repair embolisms overnight when demand is low and water potentials equalize. Under cover of darkness, water slowly refills empty vessels, pressure relaxes, and some of the broken chains are reconnected. Others prevent embolism spread by compartmentalizing vessels, sealing off damaged parts before the bubble can grow. Still others avoid the issue altogether by building new xylem each year, creating fresh pipes to replace those that fail. It is a constant battle between tension and collapse, one played out silently in every trunk and branch. This tug-of-war is most visible in the daily cycle of stress and relief. By midday, when sunlight is strongest and air driest, transpiration peaks. The pull on the xylem columns becomes extreme. Tension stretches the system, and cavitation risk rises. Trees often wilt slightly, their leaves drooping as water struggles to keep up. Then, as evening falls and transpiration slows, the pressure relaxes. At night, water moves more freely through roots and stems. Reservoirs refill, and some embolisms are healed. The tree wakes each morning with a new balance sheet of water status, ready to face the next round of evaporation. The architecture of this hydraulic system is finely tuned. Roots explore the soil, drawing water from tiny pores. Some dive deep, tapping hidden reserves, while others spread wide to capture rain as it falls. From there, the trunk acts as a conduit, a sturdy column of xylem vessels stacked like straws in a bundle. In the canopy, branches divide the flow further, sending water to every leaf. Each level must be coordinated. If roots fail, the canopy dries. If the trunk becomes blocked, the upper branches starve. If leaves lose too much too quickly, the whole system strains. It is not just pipes and flow, it is an integrated design, a whole plant plumbing network built to balance demand and supply. This architecture also dictates a tree's shape and strategy. Tall trees face greater tension because water must climb further. They counter with wider vessels or denser wood to resist cavitation. Desert trees may keep vessels narrow and tough, trading rapid flow for safety under drought. Tropical giants can afford riskier wide pipelines because rain is more reliable. Every tree is negotiating the same challenge: how to move enough water to grow without snapping its fragile columns under stress. Because water is so fundamental, it becomes the first message that shapes nearly everything else. A tree's water status influences whether stomata open or close, determining photosynthesis rates and carbon gain. It affects hormone signals, shifting growth priorities between roots and shoots. It even primes defenses, since a drought-stressed tree is more vulnerable to pests and pathogens. In many ways, water status is the master variable, the daily headline in the life of a tree. Think of it this way: a human might start the day by checking the weather before deciding whether to carry an umbrella, a coat, or sunglasses. A tree does not have clothing, but it checks its own internal weather, the tension in its xylem, before deciding how to behave. If the water columns are healthy and strong, the stomata can open wide, photosynthesis can flourish, and growth can accelerate. If the tension is too high, stomata snap shut, photosynthesis slows, and the tree slips into conservation mode. The xylem is both a highway and a warning system. One of the most poetic aspects of this hidden plumbing is that it links earth to sky. Every drop of water taken up by roots will eventually rise through the xylem and evaporate into the atmosphere. In doing so, trees help shape weather itself, recycling moisture, cooling the air, and even influencing rainfall patterns over vast regions. A forest is not just a collection of individuals quenching their thirst. It is a machine pumping water vapor back into the sky, weaving itself into the fabric of the climate. So the next time you see leaves fluttering in the heat of the day, consider the invisible struggle within. Columns of water are stretched to their limits, bubbles are threatening to form, and the tree is playing its delicate game of survival. At night, when the air cools and the forest grows still, the xylem relaxes, repairs what it can, and braces for another round. It is a story of physics and fragility, of a liquid rope that binds the deepest soil to the highest leaf. What seems like silence is really tension, pressure, and release, a hidden pulse of life that rises and falls with the sun. And all of it depends on the cohesion of water molecules and the remarkable design of the xylem highway. It may sound strange to imagine a tree carrying an electrical spark through its tissues, but that is exactly what happens. Not the crackling arcs of lightning in a thunderstorm, but something quieter, small, fleeting changes in voltage that ripple through leaves, stems, and roots. Biologists call them action potentials and slow-wave potentials, echoes of the same basic physics that runs through human nerves. In our bodies, these signals trigger muscles, thoughts, and reflexes. In trees, they trigger defenses, adjust growth, and help the plant adapt to a changing environment. It is, in its own way, quiet lightning. When a leaf is bitten by an insect, its cells are wounded. The injury causes tiny changes in ion concentrations. Calcium, potassium, and chloride move across membranes, altering the local electrical charge. This spark, though minuscule, is enough to start an action potential-like event. Just as in animals, the wave of depolarization travels down tissues, leaping from cell to cell. But unlike the blazing speed of nerves in humans, which can reach over 100 meters per second, a tree's electrical impulses are far more leisurely. They travel in the range of millimeters per second to a few centimeters per second, a pace more like a careful stroll than a sprint. Alongside these action potentials are slower cousins called slow-wave potentials. These are not sharp jolts, but lingering electrical changes that last minutes or even hours. They often follow wounding, heat stress, or drought signals. If action potentials are quick shouts, slow wave potentials are the low, sustained hums of concern that echo across a tree's tissues. Together, these electrical events allow information about local stress to spread beyond the point of impact, notifying distant parts of the plant that something has gone wrong. Hydraulic signals add another layer to this silent alert system. When a tree experiences drought or sudden heat, water pressure within the xylem shifts abruptly. Roots feel the soil drying, leaves sense the pull of evaporating water, and pressure pulses ripple through the hydraulic system. These waves can spread faster than electrical signals, alerting tissues to act before damage accumulates. In effect, a tree can feel the strain in its own water columns and send a hydraulic warning throughout its structure. Both electrical and hydraulic messages travel long distances. A bite on one leaf can trigger responses in others, even on different branches. A sudden soil drying event can be signaled all the way from root tips to the highest leaves. The distances are impressive when you consider the size of some trees. In a tall oak or a giant redwood, a signal may need to traverse tens of meters, yet it still reaches its destination with enough strength to trigger a response. The message is not instantaneous, but in the timescale of a tree's life, minutes or hours are fast enough. What do these messages actually do once they arrive? One of the most immediate responses is stomatal closure. Stomata are the tiny pores on leaf surfaces that let carbon dioxide in and water vapor out. When drought or heat signals arrive, electrical and hydraulic cues combine to persuade guard cells to shut down, reducing water loss. The cost is slower photosynthesis, but the benefit is survival under stress. This is one of the most fundamental behavioral shifts in a tree's daily life, and it is guided by the language of quiet lightning. Another outcome is the triggering of chemical defenses. Electrical signals from wounding often precede the release of volatile organic compounds or the ramping up of secondary metabolites like tannins. By sending electrical pulses ahead of chemical changes, a tree can prepare distant leaves for possible attack before the insects even arrive. It is a bit like hearing the first rumble of thunder and closing the windows before the rain hits. Signals also interact with hormones. Stress messages can trigger the production of abscisic acid, which regulates stomatal closure, or jasminates, which orchestrate defense responses against herbivores. The interplay of voltage changes, pressure waves, and hormone cascades makes tree signaling a complex web rather than a single pathway. No one part is in charge. Instead, it is an ensemble of overlapping cues, each reinforcing or modulating the others. The fascinating part is how trees integrate these different channels. Electrical signals may provide rapid local alerts, hydraulic pulses give system-wide status updates, and hormones cement longer-term changes. Together they form a communication system that is both fast enough to handle emergencies and slow enough to shape lasting responses. It is a multi-layered warning network that suits the tree's immobile, long-lived lifestyle. Scientists have even experimented with listening in. Electrodes placed on leaves can pick up faint voltage spikes when a tree is stressed. Sensitive instruments can measure pressure changes in the xylem during drought cycles. These observations confirm what theory predicts. Trees are not static organisms but responsive systems, constantly sensing and reacting to their environment with pulses of information. To appreciate this, picture a summer day in a forest. By noon, the sun is beating down, air is dry, and water is evaporating rapidly from leaves. The tree's xylem is under strain, and hydraulic pulses ripple upward, carrying the message of tension. Leaves respond by closing stomata, while electrical signals help coordinate the timing. Meanwhile, if an insect starts chewing at the edge of a leaf, voltage changes ripple outwards, warning other leaves. Chemical defenses begin to accumulate, primed by the earlier electrical alerts. The tree is quiet to the human eye, but inside it is humming with information, signals zipping from cell to cell in a slow-motion storm of communication. Calling this system quiet lightning is fitting. It is invisible, fast compared to most plant processes, and it sparks reactions across a great distance. Unlike human lightning, it does not flash or burn, but it can change the destiny of the tree, deciding whether it conserves water, resists pests, or endures a heat wave. So while you may not hear trees whispering, you can be sure they are carrying messages, not in words, but in voltage spikes and pressure pulses, in the quiet electrical storms that ripple beneath bark and branch. A forest may seem silent, but under the skin of each tree runs a hidden network of sparks, quick warnings and steady alerts, guiding the rhythm of life in the slow green world. The air of a forest is not as empty as it seems. It is thick with invisible perfumes, drifting signals and coded warnings. When a leaf is bitten, torn, or stressed, it releases more than just a faint green smell. It releases a telegraph of molecules, volatile organic compounds, or VOCs, that float away on the breeze. These airborne messages can carry information to the tree's own tissues and to its neighbors, priming defenses and sometimes even enlisting unlikely allies. It is a communication system written not in words but in sense, as delicate as it is powerful. One of the most common of these signals are greenleaf volatiles. You know them already because they are the fresh, sharp smell that bursts from grass clippings or a snapped stem. To us they are pleasant and familiar, the scent of summer lawns and garden pruning. To plants, they are alarm bells. The moment cells are wounded, enzymes break down fatty acids into small volatile compounds that evaporate rapidly into the air. These molecules, drifting from the damaged leaf, announce to surrounding tissues and neighboring plants that something, an herbivore, a storm, or even a careless deer, is causing harm. Terpenes add another layer of complexity. These molecules are larger, more diverse, and capable of lingering longer in the air. Pines, for instance, produce rich bouquets of terpenes that smell of resin and forests. Beyond fragrance, terpenes are part of a defensive strategy. Some deter insects directly, making the leaves less appetizing. Others serve as attractants for the enemies of those insects. A caterpillar munching on a leaf may inadvertently call down wasps when the leaf releases a particular terpene blend. In this way, trees and insects engage in a game of chemical espionage, where one creature's defense becomes another's dinner bell. Then there are jasminates and salicylates, hormonal signals that can move both inside the plant and through the air. Jasminates are strongly associated with herbivore defense. When leaves detect them, they ramp up the production of protective proteins and bitter compounds, arming themselves against further attack. Salicylates, on the other hand, are often tied to responses against pathogens. Together they provide a nuanced vocabulary of scents, one saying watch out for chewing mouths, the other whispering beware of infection. What makes these airborne signals so fascinating is that other plants can eavesdrop. A tree under attack is not only protecting itself, it may be inadvertently or perhaps evolutionarily designed to warn its neighbors. Studies have shown that nearby plants exposed to these VOCs often prime their defenses. They do not launch a full-scale response immediately, because that would be energetically costly. Instead, they adjust their sensitivity, ready to respond faster and stronger if the same threat arrives. It is the difference between being startled by an unexpected knock on the door and already being on edge because the dog was barking outside. The second person reacts more quickly, and in the forest, that readiness can be the difference between survival and destruction. The insect world complicates matters further. Herbivores, predators, and parasitoids all read these chemical cues in their own ways. Caterpillars may try to suppress the release of certain volatiles, masking their presence. Predatory wasps, meanwhile, have evolved to home in on those same volatiles, using them like a map to find their prey. Ladybird beetles can detect the scents of plants under aphid attack and follow the trail to a ready meal. In this strange ecological play, plants broadcast signals that can simultaneously repel attackers and recruit bodyguards. Yet this chemical telegraph has limits. Air is an unpredictable medium. Wind may scatter signals away from the intended recipients. High humidity can slow the diffusion of volatiles, while dry turbulent air can dilute them too quickly to be useful. Unlike a wired electrical signal or a hydraulic pulse confined to xylem, these airborne cues are subject to the whims of weather. A tree may send out a perfectly crafted bouquet of molecules, only for them to vanish in the breeze before reaching a neighbour. The costs of production are also significant. Making VOCs requires carbon and energy, resources that could otherwise go into growth or reproduction. Releasing them too freely could even backfire, drawing more attention from herbivores than from helpful allies. This creates an evolutionary balance. The signals must be strong enough to matter, but not so extravagant that they waste resources or invite disaster. Interestingly, the blend of volatiles is rarely simple. Plants often release complex cocktails, dozens of different compounds in varying proportions. These mixtures create a kind of chemical fingerprint that conveys specific information. A tree might release one bouquet when attacked by caterpillars, another when infected by fungi, and yet another under drought stress. Neighbours and insects alike learn to interpret these fingerprints, responding differently depending on the message. There's also a time element. Some volatiles are released immediately upon wounding, a kind of chemical scream. Others build up more slowly, sustained over hours or days, like a lingering call for reinforcements. The changing mix over time adds nuance to the signal, letting recipients know not just that there is trouble, but how long it has been going on. From the perspective of a human walking through a forest, this invisible chatter is partly accessible. We catch the strongest of these signals as scents: the crisp smell of crushed grass, the spicy tang of pine needles, the resinous odor of sap. All are VOCs meant primarily for plant and insect communication. We are merely bystanders, tuned to notice them because they happen to overlap with our own sensory world. Yet behind those scents lies an entire hidden language, rich with meaning to the creatures that depend on it. The scented telegraph changes how we think of forests. Instead of silent stands of wood, we can imagine each gust of wind as carrying whispers, leaves warning leaves, trees recruiting allies, and insects trying to outmaneuver them all. It is an ongoing conversation that we cannot hear but can sometimes smell. Like all forms of communication in the plant world, it is neither deliberate nor conscious, but it is effective. So next time the breeze carries the sharp smell of fresh greenery, consider that it may be more than just a pleasant aroma. It may be a warning cry, a coded signal, or a plea for help drifting invisibly from one plant to another. The forest air is alive with messages, carried in molecules too small to see, reminding us that silence in nature is never truly silent at all. Beneath the forest floor lies a partnership so ancient and so successful that it may well be one of the greatest collaborations in the history of life. Long before trees stretched their crowns toward the sky, long before forests darkened the continents, plants and fungi struck a deal. Plants would provide carbon in the form of sugars, and fungi would provide nutrients and water in return. That bargain is still being honoured today, and it is called mycorrhiza. The word itself means fungus root, and that is exactly what it is: a living connection between a plant's root system and a fungus's hyphae, those delicate thread-like filaments that weave through soil. Almost every plant on Earth engages in some form of mycorrhizal partnership. Without it, many species could not grow at all. the deal is so ancient that it may have been the very reason plants were able to leave the sea and colonize land more than 400 million years ago. There are two major kinds of mycorrhiza that dominate the tree world: arbuscular and ectomycorrhizal. Arbuscular mycorrhizae are the older of the two, partnering with a huge diversity of plants. Their hyphae penetrate the outer layers of root cells, forming intricate tree-like structures called arbuscules inside. These act as trading posts, where nutrients and sugars are exchanged across cell membranes. Arbuscular fungi are microscopic, invisible to the naked eye, but they are everywhere. From tropical rainforests to grasslands, they quietly feed their hosts in exchange for carbon. Ectomycorrhizae, on the other hand, form partnerships mostly with trees in temperate and boreal forests, oaks, pines, beeches and birches to name a few. Instead of entering cells, they wrap around root tips, forming a dense sheath of hyphae. From there they send out threads into the soil, dramatically extending the reach of the tree's root system. If you have ever seen mushrooms sprouting in the forest, chances are you are looking at the fruiting bodies of ectomycorrhizal fungi. These partners are often visible, reminding us that fungal networks are not merely hidden mysteries, but active, present organisms shaping the forest around us. The trade between trees and fungi is straightforward at its core. Trees provide carbon-rich sugars, the result of photosynthesis, delivered down into the roots. Fungi cannot photosynthesize, so they depend on this supply. In return, fungi deliver nutrients that trees cannot easily access on their own. Phosphorus is often the most valuable, since it moves slowly in soil and is critical for energy transfer in cells. Nitrogen, another essential nutrient, is also gathered and passed along. Beyond these, fungi help with water uptake, reaching into tiny soil pores too fine for roots to penetrate. In dry conditions, fungal hyphae can make the difference between wilting and survival. The geometry of hyphae is part of their power. Hyphae are incredibly fine, often less than a tenth the width of a root hair, and they branch endlessly. A single gram of soil can contain kilometers of these threads. Together they form a mesh network, vastly increasing the surface area available for absorption. Imagine a tree root as a main road, and fungal hyphae as the side streets and alleyways branching from it, exploring every nook of the neighborhood. Through this geometry, fungi extend the reach of a tree's root system by orders of magnitude. The forest floor becomes a living fabric of interconnected filaments, an underground net linking one organism to another. But like any trade agreement, there are costs and complications. Trees must give up a significant share of their hard-earned carbon, sometimes up to a third of their photosynthetic output, to feed their fungal partners. That is no small expense. If a fungus delivers little in return, the cost may outweigh the benefit. Cheating is possible, with fungi taking sugars but supplying minimal nutrients, or with plants attempting to limit carbon flow while still drawing benefits. This tension has shaped an evolutionary tug-of-war, where both sides constantly adjust the terms of the deal. Interestingly, trees can exercise a kind of partner choice. Roots can allocate more carbon to fungal partners that provide better nutrients, essentially rewarding good behavior. Poor performers may be starved of sugars and left to dwindle. In this way, the relationship is not blindly cooperative but regulated, with plants maintaining some control over who gets paid and how much. Fungi too can play favorites, connecting more strongly with certain hosts. This selective exchange creates a dynamic marketplace under the soil, where loyalty is earned through performance, not given unconditionally. Despite these tensions, the partnership remains astonishingly stable. It is too beneficial for either side to abandon. A tree growing without mycorrhizae is like a business without suppliers, struggling to keep up, always on the edge of collapse. A fungus without a plant host, on the other hand, soon starves. Their survival is intertwined, and the forest as we know it would collapse without their union. This partnership also creates possibilities beyond the individual. Because fungal hyphae can connect multiple trees, they form what some call the wood wide web. Through these networks, carbon, nitrogen, and even warning signals can move from one tree to another. Seedlings in deep shade may receive a trickle of sugar from older trees via fungal links. Stressed individuals may share information chemically, priming neighbours to prepare for pests or drought. Whether these connections are intentional, incidental, or somewhere in between is still debated, but the result is clear. Fungal threads help stitch the forest into a community. The story of mycorrhiza is a reminder that life is built not only on competition but on collaboration. Trees may tower over us with an air of independence, but their strength comes from unseen allies beneath the soil. Each step in a woodland falls on a living web, a fabric spun of fungal threads and rooted partnerships, older than the hills themselves. Next time you see a mushroom after rain, pause for a moment. The visible cap is just the tip of the story. Beneath it lies a hidden empire of filaments, countless threads woven into the roots of trees, engaged in trade, negotiation, and survival. It is an ancient friendship, forged in the earliest days of land plants, still thriving beneath every forest floor today. If the roots of a forest are its foundation, then the fungal threads weaving among them are its wires and pipes, linking trees into a living infrastructure. This underground network has become famous as the wood wide web, a term that captures its hidden, connective nature. Through these fungal highways, carbon, nitrogen, and even water can move between trees. Messages of stress can ripple outward, neighbours can lend or siphon resources, and the boundaries between individuals blur into something larger. The most obvious cargo in this network is carbon. Trees, after all, are factories of sugar, and they pay their fungal partners with this currency. But once inside the fungal system, those sugars do not always stay with the original partner. Hyphae often connect multiple roots, forming junctions where carbon can leak from one host to another. Sometimes this means a well-lit adult tree subsidizing a shaded seedling nearby. Other times, it may mean carbon flowing between species entirely, say, from a birch to a fir, depending on the season and who has surplus. The flows are not always generous gifts. They can be opportunistic side effects of shared pipelines. Still, the result is striking. In some forests, nearly every tree may be linked by at least one fungal thread, participating in a shared carbon economy. Nitrogen is another key traveller. Unlike carbon, which plants can manufacture, nitrogen must be scavenged from the soil. Fungi excel at this, breaking down organic matter and capturing scarce mineral forms. When connected to multiple hosts, they can effectively redistribute nitrogen across the community. This means that species better suited to acquiring nitrogen may inadvertently, or perhaps inevitably, supply others. For young seedlings, which often struggle to access enough nitrogen on their own, this fungal subsidy can be the difference between establishing roots or fading away. Water too can travel along these shared links. Hyphae are far thinner than root hairs and can bridge soil pores that roots cannot reach. When soil is patchy, dry in one pocket, moist in another, the fungal network helps even out the distribution. Experiments have shown water moving from a well-watered plant to a drought-stressed neighbour through fungal connections. The amounts are not enormous, but in the fine balance of survival, even a small trickle can keep leaves alive until the next rain. The network is not only about goods, but also about information. Stress messages can spread through roots and hyphae, altering the chemistry of connected plants. A tree attacked by insects may release defensive signals that prime its neighbours. A sudden drought experienced by one root system may ripple as a warning through shared fungal threads, nudging others to close their stomata sooner. These alerts are not conscious warnings, but they act as an early alarm system, preparing connected individuals for threats before they experience them directly. It is easy to imagine this underground web as a smooth, continuous net binding the entire forest into harmony, but the reality is patchier. Networks overlap, shift and break with time. Soil is not uniform, and fungi differ in their abilities and preferences. Some specialize in certain hosts, others are generalists. A tree may connect strongly to one fungal partner and weakly to another, creating overlapping neighborhoods rather than a single whole community network. Disturbances like fire, drought, or logging can snap links and force new connections to form. The result is more like a shifting mosaic of connections than a single universal web. These shifting patterns raise the question of who benefits and when. For a small seedling in deep shade, tapping into a fungal network can provide vital carbon and nutrients, a literal lifeline. For the older tree supplying those resources, the costs may be negligible, or may represent a burden, depending on conditions. In some cases, the flow even reverses. During autumn, deciduous trees may funnel surplus carbon through fungi into evergreens, which then repay the debt in spring when they are photosynthesizing earlier. The balance of give and take changes with the seasons, with no permanent direction of generosity. Species mix matters as well. In a diverse forest, some trees share fungal partners, while others do not. Those who belong to the same fungal guild can form tight-knit networks of exchange, while outsiders remain disconnected. This can influence which seedlings succeed, as those without access to the right fungi may struggle. Soil conditions add another layer. Acidic soils may favor certain fungi, while alkaline or nutrient-poor soils favor others. The architecture of the network depends not only on the trees above but also on the chemistry below. Even the question of cooperation versus competition is complicated. A fungal network may redistribute resources, but does that make it an altruistic system? In many cases, flows happen simply because of concentration gradients. Resources move from high to low, whether or not it benefits anyone. Sometimes the result looks cooperative, other times competitive. A large tree might draw carbon or nitrogen away from a small neighbor just as easily as it supplies one. The network is not guided by fairness, it is guided by physics and biochemistry. The outcomes, however, can still shape the survival of individuals and the structure of the forest as a whole. This ambiguity is what makes the forest network so intriguing. It is not a utopia of sharing, nor is it a ruthless battleground. It is both at once. Cooperation and competition are interwoven underground, mediated by fungi that act as both brokers and toll collectors. Each hyphal strand is a pipeline, but also a gatekeeper. Trees pay carbon to access it, and what they get back depends on the moment, the partner, and the surrounding conditions. To walk through a forest with this in mind is to see it differently. Every tree trunk becomes not just an individual, but a node in a hidden web. Every patch of moss or fallen log may conceal filaments connecting one root to another. What looks like stillness is really a shifting marketplace of sugars, nitrogen, water, and warnings, constantly moving below our feet. The forest network is not perfect, and it is not permanent. Links are built and broken, debts are paid and called in, and fungi act as the unseen mediators. Yet through these invisible threads, forests become more than the sum of their parts. A stand of trees is not merely a crowd of individuals, but a community, stitched together by hi-fi, that bridge gaps, carry messages, and remind us that even in the quiet, life is never truly solitary. One of the quiet marvels of tree life is that roots do not behave the same way toward every neighbor. Beneath the soil, where roots encounter one another in the dark, there is a subtle ability to tell kin from stranger. When a tree grows beside its relatives, its root system often shows restraint, reducing aggression, avoiding overlap, and sometimes even channeling resources toward its kin. When it grows beside unrelated trees, competition tends to sharpen. Roots expand more aggressively, seeking to claim territory and resources. This phenomenon, known as kin recognition, is one of the most surprising discoveries in modern plant science, and it changes how we think about forests. The first question is, how do trees even tell the difference? They do not have eyes or ears, but roots are highly sensitive chemical detectors. Exudates, small molecules released into the soil, carry information about identity. Each species has a characteristic blend, and even individuals within the same species may leave slightly different chemical signatures. Experiments have shown that roots can alter their growth patterns, depending on whether they detect familiar or unfamiliar cues nearby. It is not conscious recognition in the human sense, but it is a measurable and consistent response, as if roots are able to smell their family ties. For seedlings, this recognition can make the difference between life and death. A young tree germinating close to its parent faces both opportunities and dangers. On the one hand, the parent can provide support. Its roots may overlap and share fungal partners, giving the seedling access to nutrients and even a trickle of carbon. Some studies have shown seedlings faring better when they grow near related adults, benefiting from reduced competition and a more generous flow of resources through shared fungal links. On the other hand, seedlings near parents also face risks. Shaded by a tall canopy, they may struggle to photosynthesize. They may also be more vulnerable to pathogens or herbivores that specialize in that particular species, since enemies often concentrate where their host is abundant. In some cases, parental proximity is more a hindrance than a help. Whether kinship is a blessing or a curse depends heavily on the environment. In crowded, stressful conditions, help may matter more. In open, fertile conditions, the competition for light may overwhelm any advantages. This tension is at the heart of evolutionary logic. Why would a tree reduce competition with relatives, or even assist them, if that means giving up some of its own resources? The answer lies in inclusive fitness. Genes do not simply spread by producing as many offspring as possible. They also spread by helping copies of themselves survive in relatives. If aiding a sibling or child increases the odds that shared genes persist, then cooperation can be favored by natural selection. In this way, kin recognition makes evolutionary sense. A tree that competes a little less fiercely with relatives may ensure that more of its genetic line continues, even if it sacrifices some personal advantage. The neighborhood effect is another piece of the puzzle. Forests are patchy places where seedlings sprout in clusters and kin are often close together. In such neighborhoods, mutual restraint may stabilize communities. If every individual fought tooth and root against its relatives, the result might be mutual destruction, leaving the patch open for invaders. By dialing back aggression among kin, trees create conditions where related groups persist longer, even if strangers at the edges are met with greater competition. Case studies illustrate this delicate balance. In beech forests, researchers have observed that seedlings growing near their mothers receive more support via fungal networks, especially in their earliest years. The maternal trees seem to channel carbon disproportionately toward their offspring, as though subsidizing their start in life. These seedlings, in turn, are more likely to survive the vulnerable stage when light is scarce and roots are small. Douglas fir offers another famous example. In mixed stands of Douglas fir and paper birch, scientists have traced carbon moving from birch trees in the summer, when birch leaves are abundant, to fir trees shaded beneath them. Later in the season, when the fir is more active, the flow reverses. But within Douglas fir populations, the pattern shifts again. Seedlings closely related to the adults seem to receive more carbon than the unrelated seedlings, suggesting that kinship influences how much help the fungal network provides. Even small herbs show kin-like responses. In experiments with wildflowers, seedlings planted next to siblings often grew fewer roots, as if conserving space, while those beside strangers expanded their root systems aggressively, competing harder for soil nutrients. This same principle appears in trees, scaled up to the size of forests. The pattern is consistent. Related individuals are treated more gently, strangers more harshly. Of course, not all species show strong kin recognition. In some, competition is intense no matter who the neighbor is. In others, the effect is subtle or context-dependent. The forest is not a single rulebook, but a library of strategies. Some trees lean more on cooperation with kin, others rely on sheer competitive strength. Evolution has shaped each to its own environment, and kin recognition is only one of many tools. What is clear is that kinship matters in the quiet drama beneath the soil. It shapes how roots spread, how nutrients are shared, and how seedlings survive in their earliest years. It explains why forests are not simply random assortments of individuals, but layered communities where relationships stretch not just between species, but within families. For us, it is a reminder that even organisms without nervous systems or conscious thought can show behaviors that look strikingly familiar. Kin recognition in trees echoes patterns seen in animals, where siblings often show cooperation or restraint. These same evolutionary principles apply across life. Helping relatives can help yourself, if genes are the measure of success. So next time you stand in a grove of trees, imagine the hidden family ties beneath your feet. Roots are not just searching for water and nutrients, they are feeling for neighbors, sensing kinship, and deciding how fiercely to compete. Each tree is not only an individual but also part of a lineage, its survival bound to the fate of relatives nearby. In that unseen world of roots and fungi, family matters, even when it is carried not in words or thoughts, but in the silent chemistry of the soil. Forests may seem peaceful, but beneath the calm canopy lies a quiet contest. Trees stand shoulder to shoulder, their crowns brushing against one another, their roots interlacing beneath the soil, and all the while they are competing for the essentials of life: light, water, and nutrients. Unlike animals, they cannot move to new territory, so they must fight their battles where they are planted. The struggle is rarely visible, but every tree is a strategist shaping its growth and chemistry to outmaneuver its rivals. Light is often the most hotly contested prize. In dense forests, sunlight trickles down like coins through the cracks of a floorboard, and every leaf is positioned to grab what it can. Tall trees spread broad crowns that shade out younger competitors, forcing them to live in the dim understory. Some seedlings adapt by tolerating shade, biding their time until a gap in the canopy opens. Others stretch desperately upward, thin and spindly, racing toward a rare shaft of light. Each forest has its hierarchy, the giants above soaking in the riches, and the underlings below, surviving on scraps. The architecture of trees, the length of branches, the angle of leaves, the density of foliage, is a record of this ongoing battle for light. Water is another contested currency. Roots dive deep, spread wide, and sometimes interlock in fierce competition for moisture. In dry seasons, the advantage often goes to the trees with deeper taproots that can sip from hidden reserves. Shallow-rooted neighbors may wilt and shed leaves, unable to match the reach of their rivals. Yet wide, shallow roots have their moments too, quickly absorbing rainfall before it can sink deeper. In this way, root systems carve the soil into territories, some overlapping, some exclusive, each drawing from the same underground reservoir. Nutrients, though invisible, are just as fiercely fought over. Nitrogen, phosphorus, potassium, and a suite of trace minerals are vital, but soils are not evenly generous. Trees release enzymes and acids to free these elements from organic matter or mineral particles. Roots and fungi then gather them before competitors can. This chemical scavenging is a race, and the first to capture the nutrient wins. Unlike light, which can be shared by layers of foliage, nutrients are zero-sum. What one root absorbs is gone for the others. Sometimes competition takes a sharper edge through allelopathy, the chemical warfare of the plant world. Certain trees release toxins into the soil or air that suppress the growth of competitors. The black walnut is a classic example. Its roots and leaves exude juglone, a compound that inhibits many neighboring plants. Gardens planted beneath walnut trees often look strangely barren. A sensitive species struggle to grow. Eucalyptus trees are also notorious for producing oils that inhibit seedlings around them, creating open, fragrant groves where rivals are few. These chemicals are not about dialogue or cooperation. They are weapons, ensuring that the tree casting them holds its ground with less interference. Even when chemical weapons are not involved, roots themselves can act as silent fences. Trees carefully adjust where their roots grow, expanding aggressively into unoccupied soil, but retreating or redirecting when they encounter resistance. Some species are remarkably strategic, placing roots away from their own kin to reduce competition, but expanding with vigor against strangers. In places where space is tight, roots can intertwine in tangles that are less cooperation than an uneasy truce, each tree probing for an opening, each wary of surrendering ground. The balance between sharing and competition is complex. Through fungal networks, trees may exchange carbon or nutrients, helping neighbors survive stress. But that same fungal connection can also be a battleground, with stronger trees drawing more than they contribute. What looks like generosity one season can shift to exploitation the next. The forest does not run on morals, but on context. Cooperation may dominate in times of stress when neighbors' survival strengthens the whole community, while competition takes the lead when resources are abundant and individuals can afford to push ahead. This shifting balance is visible in how forests recover from disturbance. After a storm creates a gap, seedlings rush to fill the open space. They compete fiercely, each racing for the new light. Over time, some emerge as winners, overshadowing the rest. Yet once the canopy closes again, cooperation through fungal connections and root sharing helps stabilize the new community. The forest is an ebb and flow of rivalry and alliance, never fixed in one state for long. The quiet rivalries of trees shape the landscapes we see. The towering canopy of tropical rainforests, where every meter of space is occupied, is a testament to relentless competition for light. The wide, open spacing of savanna trees reflects competition for water, each holding territory around its roots. In temperate woodlands, the patchwork of species arises from chemical interactions, root strategies, and shifting balances of power over centuries. To us, the forest may feel tranquil, a green cathedral of stillness. But to the trees themselves, life is a daily contest, fought not with claws or teeth, but with architecture, chemistry, and patience. Each branch angled for sunlight, each root probing for moisture, each molecule of juglone or terpene drifting into the soil is part of this unseen struggle. And yet, the rivalry is not absolute. Without some degree of sharing, forest would collapse. Without competition, they would stagnate. The secret is in the balance, a dynamic dance where trees sometimes cooperate, sometimes battle, and always adapt to the conditions around them. The shaded rivalries beneath the canopy are the engine that keeps forests alive, shaping not only who survives but how entire ecosystems evolve. So when you step into a woodland and see shafts of light piercing the leaves, or notice the barren ground beneath a walnut, remember the contest unfolding beyond sight. The forest is not silent. It is a theatre of rivalry, chemical strategy, and shifting alliances, a place where every tree is both neighbour and competitor, playing its part in the long, slow game of survival. In the great stillness of a forest, every tree is under siege. Insects chew, fungi invade, bacteria slip between cells, and deer strip bark or browse on young shoots. To survive, trees have built an arsenal of defences, some permanent, others deployed only when danger strikes. This constant negotiation between attack and protection shapes not only the fate of individual trees, but the balance of entire ecosystems. One strategy is to keep defences always on. Some trees maintain high levels of protective chemicals at all times, like tannins that make leaves bitter, or linen that makes wood tough to chew. Pines and spruces rely on sticky resins, which ooze from wounds and trap invading insects. Thorns, spines, and thick bark all fall into this category. Physical and chemical armour that stands ready, whether or not an enemy is present. Always-on defences are reliable, but they are expensive. Every molecule of tannin or drop of resin is carbon that could have gone into growth or reproduction. The alternative is induced defence, producing protection only when needed. When a caterpillar takes a bite, a tree may respond by activating enzymes that flood the leaf with toxins. When fungi breach bark, antimicrobial compounds can be produced locally. This strategy saves resources during peaceful times, but demands quick detection and response when an attack begins. Induced defences are like calling in reinforcements only when the first shots are fired. The balance between constant and induced defences depends on the environment. In places with relentless herbivory, like tropical forests where insects are active year-round, always-on defences are more common. In seasonal climates where attacks are sporadic, induced defences are often favoured. Evolution shapes each species' strategy according to the risks and costs of its world. But trees also have something more subtle in their toolkit: priming. This is a kind of memory that does not rely on nerves or brains, but on chemical marks and physiological changes. When a tree experiences an attack once, it often responds faster and stronger the next time. Priming does not mean keeping defences constantly active, but rather keeping them on standby, easier to switch on at the next sign of trouble. It is as though the tree has rehearsed the battle once and is better prepared for the sequel. Priming can last for days, weeks, or even longer. Some evidence suggests that seeds may carry traces of parental priming, passing on readiness to the next generation. This raises the possibility that trees not only defend themselves, but prepare their descendants for the threats they faced. Without thoughts or memories, they still achieve something akin to experience shaping future behaviour. The signalling pathways involved are intricate. Jasmonic acid is central to defences against chewing herbivores. When insects bite, jasmonate levels spike, turning on genes that produce toxins and protein inhibitors that disrupt digestion. Salicylic acid, in contrast, is more involved in defense against pathogens such as fungi and bacteria. These pathways do not work in isolation. They crosstalk, sometimes amplifying one another, sometimes interfering. For example, activation of jasmonate defenses can suppress salicylate responses, and vice versa. This balancing act ensures that resources are not wasted fighting every possible enemy at once, but are targeted toward the most immediate threat. This biochemical tug-of-war creates trade-offs that ripple through a tree's life. If an oak devotes resources to jasmonate-driven defenses against caterpillars, it may become temporarily more vulnerable to a fungal infection. If it primes too strongly in one direction, it risks imbalance. The coordination of these pathways is part of the hidden sophistication of plant life, a kind of decision-making written in hormones and enzymes. Interestingly, defense is rarely confined to the individual. A tree under attack often releases volatile organic compounds into the air, alerting nearby trees. Those neighbors, detecting the scent, may prime their own defenses before the attacker arrives. This spillover effect benefits the community but comes at a cost to the signaler. Releasing volatiles takes energy and can sometimes attract more attention from herbivores. Yet the advantage of a prepared neighborhood may outweigh the risk. If the stand of trees survives together, each has a better chance of long-term survival. This community-level defense creates strange dynamics. A tree that benefits from its neighbor's signals without contributing any of its own is effectively freeloading, saved by others' warnings. Over time, natural selection balances these interactions, but the system is not perfect. Forests are patchworks of sharers, cheaters, and everything in between. What matters is that enough signals are exchanged to tilt the odds in favor of survival. Defenses also involve recruiting allies. The volatile compounds released by attacked leaves can attract predators or parasitoids of herbivores. A caterpillar chewing through a leaf may suddenly find itself under assault from a wasp, guided by the scent the leaf itself released. In this way, trees outsource part of their defense to insects, using chemical signals as beacons to call in reinforcements. It is a remarkable twist. What begins as damage becomes a trap set for the attacker. For us, these defenses remind us that stillness does not equal passivity. A forest may appear serene, but at any moment invisible battles are being fought at the molecular level. Defenses are switched on and off. Signals are released into the air and soil, and trees remember past encounters in ways that influence their futures. This hidden drama shapes which trees thrive, which fail, and how entire ecosystems evolve. So the next time you smell the sharp tang of pine resin, or the sweet aroma of crushed leaves, think of it as part of an ancient defense system, perfected through millions of years of trial and error. Trees may not roar, snap, or flee, but they are armed all the same, standing in quiet armor. And when trouble comes again, they will remember, not in thoughts, but in chemical readiness, prepared to meet the challenge with defenses primed and waiting. When we think of memory, we usually imagine a brain, a web of neurons firing, storing impressions of sights, sounds, and experiences. Trees, of course, have no brains, no nervous systems, no conscious recall. Yet in their own way, they remember. Their memories are written not in neurons, but in molecules, tissues, and even the wood itself. These are not memories in the human sense, but they serve the same purpose, allowing past experiences to shape future responses. One form of memory is epigenetic. At the cellular level, trees can leave chemical marks on their DNA or on the proteins that package it. These marks do not change the genetic code itself, but adjust how genes are expressed. When a tree endures drought, for example, certain stress response genes may be turned up or kept at the ready. The epigenetic marks act as bookmarks, making it easier to access those responses when the stress returns. In this way, the tree remembers drought, not by thinking about it, but by altering the likelihood of responding quickly in the future. Such memories can last weeks, months, or even years, depending on how stable the marks are. In some cases, they may even pass to seeds, giving the next generation a head start against the same stress. A seedling born from a drought-stressed parent may germinate with a slightly heightened sensitivity to water scarcity, primed for a world that resembles the challenges of its parent's life. This inheritance is not absolute. It fades over time, but it shows that trees can carry echoes of the past into the future without a single neuron involved. Another archive of memory lies in tree rings. Each year, a tree lays down new wood, and the thickness, density, and chemical composition of that ring record the conditions of that season. A wide, light ring may mark a year of abundant rain and sunlight. A narrow, dark ring may signal drought, fire, or insect infestation. Scientists who study dendrochronology can read these rings like a diary, reconstructing centuries of climate history from the trunks of long-lived trees. Fires leave scars etched into the wood as blackened seams that can be dated precisely. Pest outbreaks show up as sudden narrowings when leaves were lost and photosynthesis slowed. In this way, a tree keeps an unbroken record of the world it has lived through, one line at a time. These rings are not just passive records. The structural changes they embody influence the tree's physiology going forward. A year of narrow rings may mean reduced reserves, affecting how strongly the tree can flush new leaves the following spring. Past experiences etched into the wood shape what the tree is capable of next. The diary is also a blueprint, one that constrains and guides future growth. Memory in trees can also look like habit. Repeated cues often lead to quicker, stronger responses, as if the tree has rehearsed for them. A leaf that has been attacked once may respond faster to a second attack because signaling pathways have been primed. A root exposed to cycles of drought may close its stomata more swiftly when water scarcity returns. This kind of physiological learning is not conscious but is remarkably effective. The tree's body becomes trained, its responses sharpened by practice. Yet these memories are not infinite. They fade with time, and they come with trade-offs. A tree primed to defend against herbivores may invest more in toxins, but at the cost of slower growth. A tree trained by drought to be conservative with water may close stomata quickly, protecting itself but also limiting photosynthesis and carbon gain. There is no free lunch in biology. Every advantage carries its price, and memory must be balanced with flexibility. The fading of memory is important. If a tree held on too tightly to past conditions, it might fail to adjust when the environment changed. A tree that constantly expected drought might miss opportunities during wet years, growing less than its competitors. By letting some memories decay, trees keep themselves adaptable. Epigenetic marks are gradually erased, defensive priming resets, and old rings are buried deeper in the trunk, their lessons stored but no longer directly active. Forgetting for a tree is as vital as remembering. This balance between memory and forgetting echoes our own experiences. We too cannot hold every detail of life in perfect recall. We remember what matters, what prepares us for the future, and let go of the rest. Trees follow the same principle, but their memories are written in wood and molecules rather than thoughts. To walk through a forest is to walk among living libraries. Each trunk is a history book, recording decades or centuries of climate, fire, flood, and growth. Each leaf carries traces of stresses endured, tuned by past encounters. Each root knows, in its own chemical way, the patterns of soil moisture and nutrient flow. Memory without a brain may sound alien, but it is happening all around us, in every forest, field, and garden. So next time you rest your hand on the bark of an old oak, consider the centuries it remembers. Its wood carries droughts long past, storms that stripped branches, fires that scarred but did not kill. Its cells bear chemical echoes of struggles and recoveries. Its leaves respond with reflexes honed by experience. Though it cannot tell its story in words, it has lived it, recorded it, and continues to act upon it. Memory takes many forms in nature, and the silent recollections of trees are among the most enduring of all. In the forest, time is kept not by clocks or calendars, but by the rhythm of the seasons. Trees live by a schedule written in sunlight, temperature, and memory of winters past. This schedule is called phenology, the science of seasonal timing. It is the reason buds open in spring, flowers appear at just the right moment, leaves fall in autumn, and trunks rest quietly through the cold of winter. To the casual eye, these events may look simple, but they are finely tuned, and the slightest misstep can ripple through the entire forest community. One of the first great milestones each year is bud break. After a long winter of dormancy, when growth pauses and tissues harden against frost, buds wait for the signal to open. Inside those tiny packages are the leaves or flowers of the coming season, pre-formed but on hold. The trigger to burst forth is a mix of cues. Photoperiod, the length of daylight, provides a reliable signal that spring is advancing. Temperature adds nuance, ensuring that buds do not open during a brief warm spell in midwinter. Many species also require chilling, weeks of sustained cold that act as a reset button, convincing the tree that true winter has passed. Only when these requirements align do buds swell, break, and unfurl into the new season. The choreography of bud break is not just about individual survival, it is about synchrony. When many trees in a forest leaf out together, they create a sudden flush of green that floods the canopy with shade. This benefits the whole community, reducing the window in which early pests or pathogens can thrive unchecked. In flowering species, synchrony ensures that pollinators find abundant resources at the same time, maximizing cross-pollination. A lone tree flowering weeks before its neighbors might find itself blooming in vain, its pollen drifting into emptiness. Leaf-out follows closely, transforming bare branches into solar panels. This timing is critical. Too early and tender leaves may be burned by a late frost, a quiet catastrophe that strips photosynthetic potential for the entire season. Too late, and the tree loses valuable weeks of energy capture. The balance is delicate. In temperate zones, a single cold snap in April can undo months of preparation, forcing trees to regrow leaves at great cost if they can manage it at all. Whole landscapes may appear scorched brown in spring after such events, as if the forest has sighed in disappointment. Dormancy at the other end of the cycle is equally important. As autumn approaches, days shorten and temperatures fall. Trees begin to dismantle their chlorophyll, drawing nutrients back into trunks and roots for storage. Leaves blaze with reds and yellows before falling away, reducing water loss and preventing damage from snow or ice. Dormancy is not simply a nap. It is a carefully managed state of reduced activity. Buds are set for next year, tissues are hardened, and metabolism slows to a minimum. Like travelers huddling against winter storms, trees endure by conserving what they can until warmth returns. The triggers for these events vary by species and region. Some trees rely heavily on photoperiod, which is stable year after year and unaffected by short-term weather. Others put more weight on temperature, giving them flexibility to respond to unusual seasons. Still others require both cues together, reducing the risk of mistiming. Chilling requirements ensure that trees do not rush into growth after a few mild days in January. Without that safeguard, a premature leaf-out could be wiped out by the inevitable return of frost. Synchrony within a community brings both advantages and risks. Where many trees flower at once, pollinators thrive, seeds disperse widely, and genetic mixing increases. But synchrony also means shared vulnerability. If the entire community is tricked into early growth by an unusually warm spring and then struck by frost, the losses are catastrophic. No single species is spared, and the forest suffers as a whole. In this sense, timing is both a shield and a gamble. Mistiming is becoming more common as climate patterns shift. Warmer springs tempt buds to open earlier, but frosts have not disappeared. In some regions, late freezes are now more frequent, leaving orchards and forests alike vulnerable. Pollinator cycles may drift out of alignment, with insects arriving before or after flowers are available. Migratory birds may return to find that peak leaf flush, and caterpillar abundance have already passed. These quiet mismatches ripple outward, affecting entire food webs. For a tree, a mistimed event can mean more than just lost growth. If flowers are destroyed by frost, reproduction for that year may fail. If leaves are lost early, carbon reserves may dwindle, leaving less to fuel defenses or winter survival. These are not dramatic deaths, but slow erosions of strength, weakening trees over years and decades. The clock of the woods ticks steadily, but if its gears fall out of sync, the cost can accumulate quietly, almost invisibly, until the resilience of the forest falters. Despite these risks, the resilience of trees is remarkable. Many species hedge their bets, staggering leaf out across individuals so that not every tree in a population is exposed to the same danger. Others produce more buds than they need, a reserve in case some are lost. Evolution has shaped a diversity of strategies, ensuring that no single cold snap or warm spell can wipe out an entire lineage. The forest clock is not rigid but adaptable, capable of adjusting to shifts over time. For those who watch closely, phenology is a window into the forest's heartbeat. The sudden green of spring, the blaze of autumn, the bare patience of winter, each marks a turning of the wheel. Scientists and citizens alike track these moments, using them to chart the progress of climate change, to predict harvests, and to understand how ecosystems respond to shifting seasons. Every bud and leaf is both a biological event and a piece of a larger calendar, written not in numbers but in living tissue. To stand in a forest in spring is to feel this clock in motion. Buds swell, flowers open, and leaves unfurl in a rush of synchronized growth. It is a reminder that time in nature is not abstract but embodied. Trees do not own watches, yet they know exactly when to wake, when to work, and when to rest. Their clock is ancient, reliable, and endlessly fascinating, ticking through centuries as quietly as the breeze. And though it may falter under the strain of a changing climate, for now the forest still keeps time, steady and sure, with every leaf that falls and every bud that opens. Old-growth forests are not just collections of big trees. They are layered cathedrals of life, built slowly over centuries. Step inside one and you enter a vertical city, with neighborhoods stacked from the dark soil to the sunlit crowns. Each layer has its own residents, its own rules, and its own microclimates. The architecture is the result of countless years of growth, death, and renewal, and it shapes how signals, resources, and opportunities flow through the forest. At the bottom lies the understory, the shaded floor where little light filters through. Here, young seedlings wait patiently, often for decades, surviving on scraps of sunlight that leak between leaves above. These small trees are adapted to shade, keeping their metabolism slow and frugal. They are like renters in a dim basement apartment, waiting for the chance to move upstairs. Ferns, shrubs, and saplings dominate this level, forming the quiet foundation of the forest. Above them, the mid-story holds small trees and the lower branches of taller ones. This is a transition zone, where light is still limited but more abundant than on the floor. Here, saplings can stretch upward, slowly entering the competition for space. Some may never make it, shaded too long and too thoroughly. Others bide their time until a gap appears, and then surge upward with sudden growth, as if they had been waiting all along with energy in reserve. Higher still is the canopy, a continuous green roof where crowns of mature trees interlock. This layer captures most of the sunlight and dominates the forest economy. It is busy, noisy with birds and insects, rich with leaves photosynthesizing at full tilt. The canopy is the power plant of the forest, where sugars are minted and fed down to trunks and roots. For the trees that make it this far, space here is everything. Each crown spreads as wide as it can, jockeying for position, twisting branches toward open light, shading rivals, and maintaining dominance over the floor below. And then there are the emergent crowns, the giants that rise above all the rest. These trees stand like skyscrapers, catching full sunlight on all sides. They endure buffeting winds, lightning strikes, and storms. But their reward is unrestricted access to light. From the top of an emergent crown, a tree may command views over kilometers of forest, its branches laden with epiphytes, mosses, and even small animals that treat its crown as a home in the sky. Only a few species can achieve this height, and fewer still survive long enough to hold their crowns aloft. Within these layers, microclimates abound. The forest floor is cool, damp, and sheltered. Mid-story air is warmer, with dappled sunlight. The canopy is bright, windy, and variable. Signals drift differently in each zone. Volatile chemicals released from a leaf may travel easily across the canopy, but dissipate before reaching the floor. Hydraulic signals in roots may benefit understory saplings more than canopy giants. Even fungal networks respond to the patchiness, creating overlapping maps of connection that mirror the layers above. Communication in an old-growth forest is not uniform, it is filtered by architecture. Gaps are the great invitations in this vertical city. When a storm knocks down a giant, sunlight pours into the hole it leaves, transforming a dark understory into a sudden opportunity. Seedlings that have been waiting for decades surge upward, racing to fill the space. Different species exploit gaps of different sizes. Some need wide, sunlit openings, while others slip into smaller breaks. Over time, these gaps ensure renewal, preventing the forest from freezing into stasis. Every fall of a giant is also the rise of newcomers. Elders often facilitate this process in surprising ways. Large trees moderate the climate of their neighborhoods, buffering temperature extremes and holding moisture in the air. Their roots enrich the soil, their fallen leaves add nutrients, and their fungal partners link seedlings into the wider network. A sapling growing near an old parent may benefit from this sheltered microclimate and shared infrastructure. The giants, in their slow way, make life a little easier for the next generation. Deadwood plays a vital role in this architecture too. A fallen log is not simply debris, but a living infrastructure in its own right. Nurse logs, as they are called, cradle seedlings in their decaying mass. Mosses cover them, fungi colonize them, and roots sink into the softened wood. Elevated above the forest floor, seedlings on nurse logs avoid some of the pathogens and competition that plague soil-level germination. In the Pacific Northwest, entire groves of hemlocks and cedars can trace their origins back to nurse logs, long rotted away but still shaping the forest through the offspring they nurtured. Even standing dead trees, snags, serve critical roles. They provide homes for birds, bats, and insects, and their cavities eventually collect soil and moisture, supporting plants in unexpected places. Slowly, they shed bark and branches, returning nutrients to the cycle. Death in an old-growth forest is never the end of usefulness. It is simply another stage in the architecture, one that extends life by creating habitats and opportunities for others. Over centuries, this layering, gapping, and recycling builds a structure that is as dynamic as it is stable. Old-growth forests are not static relics, but living cities under constant renovation. Trees rise, fall, and are replaced. Light and nutrients shift, creating opportunities and risks. Signals weave through air, soil, and fungal threads, shaped by the spaces they must cross. The forest is at once ancient and new, held together by the architecture of its community. To stand among these giants is to feel both humility and awe. Each trunk is a pillar, each crown a rooftop garden, each fallen log a nursery. The forest is not a random tangle but a layered system, refined by time, death, and rebirth. From floor to canopy, from sapling to snag, the architecture of old-growth forests is a masterpiece of nature's slow design. an ever-changing structure that sustains life in its many forms and whispers its stories across centuries. In the life of a forest, disturbance is not an exception but an inevitability. Storms tear through with violent winds, fires sweep across the landscape, pests arrive in waves, and droughts test every root and leaf. To us, such events might look like catastrophe, but to a forest they are part of its long rhythm. Trees have evolved not only to endure disturbances, but in many cases to use them as opportunities for renewal. After the storm comes a period of quiet triage, then regrowth, and eventually a reshaping of the community that can last for decades or even centuries. The first moments after disturbance are filled with signals. When a fire scorches bark or a branch is broken by wind, trees immediately shift their internal chemistry. Electrical pulses and hydraulic pressure changes rush through tissues, warning distant leaves and roots of injury. Hormones spike, stress proteins surge, and volatile compounds drift into the air. These signals are a form of triage, mobilizing defenses where they are still intact, sealing wounds, and allocating resources to protect what remains. Neighbors may pick up on these airborne messages, adjusting their own physiology to brace for spreading fire, hungry insects, or the sudden change in microclimate created by fallen giants. Different trees have different strategies for what comes next. Some rely on serotiny, the release of seeds triggered by fire. Serotinous cones of lodgepole pine or certain eucalyptus species remain sealed with resin until intense heat opens them. When flames pass, thousands of seeds rain down onto freshly cleared soil, ready to sprout in a landscape where competition has been temporarily removed. What looks like destruction to us is, for these trees, a reset button that ensures the next generation arrives right on cue. Other species put their faith in resprouting. Oaks, chestnuts, and willows, among many others, can push out new shoots from roots, stumps, or buried buds after their above-ground tissues are damaged. Even if the canopy burns or breaks, the living tissues below ground often survive, sending up shoots to reclaim space. In this way, old roots anchor new life, and a tree's body becomes both casualty and parent in its own recovery. Seed banks add another layer of resilience. Many plants, including some trees, keep a store of viable seeds lying dormant in the soil. These seeds can wait years, even decades, for the right conditions to germinate. Fire, flood, or canopy gaps can trigger their awakening. Suddenly, a long silent reserve bursts to life, filling bare ground with seedlings that might otherwise never have had a chance. The soil is not just dirt, it is a memory of past generations, waiting for the right moment to speak again. Fungi also play a crucial role in the reset. When disturbance clears vegetation, the underground mycorrhizal networks may be damaged or destroyed. But fungi are quick to recolonize, sending spores into the air and hyphae through the soil. Their return is essential, reconnecting roots to the nutrients and water they need. In some cases, fire-adapted fungi thrive in post-burn soil, forming partnerships with pioneer plants that stabilize the ecosystem. The fungal reset is invisible to us, but central to the forest's recovery, ensuring that new roots do not grow in isolation, but are stitched once again into the underground web. Recovery unfolds not in weeks or months, but in decades, through a process called succession. In the first years after disturbance, fast-growing pioneer species race to colonize open ground. These are often short-lived trees or shrubs, adapted to thrive in light-filled, nutrient-poor conditions. They stabilize soil, add organic matter, and create shade. Over time, slower-growing, longer-lived species move in, establishing beneath the pioneers and eventually overtopping them. What began as a raw clearing becomes layer by layer a new forest. This conversation between species unfolds slowly, each group preparing the stage for the next. Succession is not a straight line. It is shaped by chance events, climate, and the specific nature of the disturbance. A fire that burns hot may kill seed banks as well as adults, forcing recovery to come from distant dispersers. A windstorm that topples some but not all trees may create patchy gaps that fill differently. An insect outbreak that targets one species may open opportunities for others, permanently altering the community. Each disturbance writes a new story, and no two recoveries are quite the same. The resilience of forests lies in their ability to absorb these shocks and return to some version of themselves. A healthy forest can endure fire, pests, or storms, and still reassemble its structure over time. Its species have evolved for such trials, and its networks of roots and fungi help buffer the impacts. But resilience has limits. Sometimes disturbance tips a forest into a new state entirely, a regime shift. Repeated fires may favor grasses over trees, turning woodland into savanna. Invasive pests may wipe out keystone species, unraveling networks that held the community together. Climate change, by amplifying stress, makes such shifts more likely. To the human eye, these transformations can feel tragic, as if something ancient has been lost. Yet from nature's perspective, they are simply change. Life reorganizes, finds new balances, and moves forward. The challenge for us is that these shifts may no longer resemble the forests we once knew. Still, there is beauty in the resilience that remains. Walk through a burned forest a year later, and you may see carpets of seedlings, flowers blooming where ash once lay, and shoots rising from blackened stumps. 10 years later, young stands crowd the sky, vigorous and green. A century later, the forest may be indistinguishable from its predecessor, carrying scars deep in its rings, but thriving once again. Forests teach us that disturbance is not the end of the story, but part of it. Storms, fires, and pests are not just destroyers, they are sculptors, reshaping ecosystems, clearing space, and renewing life. The signals trees send in those first desperate moments are not cries of defeat, but the opening lines of recovery. In their ability to resprout, reseed, and reset, forests remind us of nature's patience. Survival is not about avoiding disaster, but about learning how to live after it. Not all trees live in the comfort of temperate woodlands with steady rains and gentle seasons. Some grow on the margins of possibility, in places where survival seems improbable. Mangroves cling to salty coasts. Desert trees endure long months of thirst, and boreal forests withstand winters so cold that water itself becomes unavailable. Yet in each case, trees have evolved ingenious ways to read their environments and respond to messages written in tide, drought, or frost. Their lives are proof that even at the edges of habitability, persistence is possible. Mangroves are perhaps the most iconic edge dwellers. They root themselves in tidal zones where saltwater floods twice a day, a setting that would kill most plants. Salt is a double-edged sword, necessary in small amounts but lethal in excess. Mangroves have developed several strategies to manage it. Some excrete salt through glands in their leaves, leaving behind tiny crystals that sparkle in the sun. Others filter salt at the root level, allowing only fresh water into their tissues. In extreme cases, they simply compartmentalize salt into sacrificial leaves that eventually drop away, carrying the excess with them. These tricks allow mangroves to thrive where few other trees dare. Breathing in waterlogged soil presents another problem. Oxygen cannot diffuse easily through saturated mud, so mangroves push up pneumatophores, strange snorkel-like roots that poke above the surface. These structures absorb oxygen directly from the air, feeding it down to the buried tissues. Walk through a mangrove swamp, and you see a spiky forest below the forest, hundreds of root spires breaking the surface like candles on a dark cake. Together with their stilt-like support roots, these adaptations anchor the trees against tides and storms while keeping them supplied with breath. Timing is everything in a tidal world. Mangroves must match their growth to rhythms of inundation and exposure. Seeds often germinate while still attached to the parent tree, growing into elongated propagules that drop into the water and float until they lodge in a suitable spot. This strategy ensures that seedlings already have a head start, their roots and shoots ready to deploy the moment they land. It is a bold gamble in a harsh environment, but it works. Mangroves form dense, resilient stands that shelter coastlines and nurture marine life. From the water's edge we move to the desert, where the challenge is not salt but scarcity. Rain falls rarely and unpredictably, and when it comes, it may vanish within hours. Trees that survive here are masters of timing. Some, like acacias, have roots that plunge astonishing depths into the soil, tapping aquifers unreachable to other plants. Others spread shallow, wide root systems to capture every drop of sudden rainfall before it evaporates. Both strategies hinge on detecting water pulses and responding quickly. Desert growth is cautious, calibrated to conserve rather than expend. Leaves may be tiny, waxy, or even absent, replaced by green stems that photosynthesize with less surface area exposed. Stomata open only briefly, often at night to minimize water loss. Some desert trees enter dormancy during dry years, pausing growth almost completely until conditions improve. It is as if they can read the message written in the sky, clouds forming, humidity rising, and choose their moment to act. Even reproduction is tuned to scarcity. Seeds often lie dormant for years, waiting for the rare rainfall that ensures a chance of establishment. When that moment comes, germination is explosive, carpeting the desert floor with new life. Yet many of these seedlings will perish if the rains do not last, leaving only a lucky few to continue. Survival here is not guaranteed, but for those that succeed, the reward is space and freedom from dense competition. Now imagine the opposite extreme, the boreal forest stretching across northern latitudes where winters are long and punishing. Here the challenge is not lack of water, but too much of it in the wrong form. For months, soils are locked in ice, and liquid water is unavailable even though snow blankets the ground. Trees endure by slowing metabolism to a crawl, conserving resources until thaw returns. The hydraulics of freeze and thaw create their own stresses. Water inside xylem can freeze, and when it thaws, bubbles may form, embolisms that block flow. Boreal trees counter this with narrow xylem vessels that reduce the risk of cavitation, sacrificing rapid water transport for safety. In spring, as the thaw comes, these vessels are tested. Some burst, forcing the tree to grow new ones quickly. The cycle repeats year after year, a reminder that survival in cold regions is not about avoiding damage, but about repairing it reliably. The growing season in boreal forests is short, sometimes only a few months. Trees respond with rapid bursts of activity, photosynthesizing at high rates during the endless daylight of summer. Leaves are often needle-like, conserving water and resisting frost, while evergreen strategies allow photosynthesis to begin as soon as temperatures rise above freezing. Each year is a sprint, and trees must make the most of it before winter clamps down again. Despite the differences among mangroves, desert dwellers, and boreal giants, their strategies converge on a few themes. All manage resources with extreme care, whether it is salt, water, or heat. All rely on timing, attuning their growth and reproduction to the rhythms of their harsh environment, and all show that resilience is not about thriving in comfort, but about adapting to limits. These edge habitats also remind us of the broader role trees play. Mangroves buffer coasts against storms and store vast amounts of carbon in their soils. desert trees anchor fragile ecosystems, preventing erosion and offering shade and shelter. Boreal forests form one of the largest biomes on Earth, storing immense carbon stocks and shaping the global climate. Their survival strategies are not just curiosities, but critical elements of planetary health. To stand among them is to witness ingenuity written in bark, leaf, and root. A mangrove filtering salt water, a desert acacia stretching roots deep into rock, a boreal spruce waiting out another freeze. Each is an answer to the question of how life persists at the limits. They do not flourish despite the edges. They flourish because of them, turning hardship into opportunity and writing resilience into the very fabric of the forest. Forests may all be green at a glance, but the conversations inside them differ profoundly depending on where they grow. A tropical rainforest with its thundering biodiversity speaks in a different language than a temperate woodland where just a handful of species dominate. Both are intricate systems of exchange, signaling and survival, but their rhythms, complexity and strategies vary like two dialects of the same ancient tongue. In the tropics, biodiversity density is staggering. A single hectare may host hundreds of tree species, each with its own fungal partners, chemical signals, and ecological quirks. The networks here are like vast cities with countless voices, overlapping and sometimes interfering with one another. Partner specificity can be high. Certain trees may rely on very particular fungi, pollinators, or dispersers, creating specialized alliances. At the same time, the density of species means that every tree is surrounded by neighbors who are mostly strangers, not relatives. This shifts the dynamics of competition, cooperation, and communication. In such crowded conditions, signals are not always private. They spill into a cacophony of chemical noise. Contrast this with a temperate forest, where species richness is lower. A European beech woodland, for example, may be dominated by just a few tree species spread across wide expanses. Networks here are simpler, with fungal partners often shared among large groups of trees. Neighborhoods are more stable, and kinship may play a stronger role, because relatives are more likely to grow near one another. The forest conversation is quieter, more focused, less muddled by the sheer density of competing signals. Nutrient cycling adds another layer of contrast. In the tropics, warmth and moisture fuel rapid decay. Leaves, branches, and even large logs break down in months or years, returning nutrients swiftly to the soil. This means resources are constantly being recycled, and trees must stay tightly plugged into the cycle or risk being left behind. It also means roots and fungi are in perpetual motion, racing to capture nutrients the moment they are released. Communication here is often about speed. When to grow, when to fruit, when to flush new leaves, all dictated by the rapid tempo of resource turnover. Temperate soils tell a different story. Cooler conditions slow decay, allowing organic matter to accumulate. Nutrients may be tied up in leaf litter for years before they are released. The result is a slower, steadier pace of cycling, with trees relying heavily on fungi to unlock nutrients bound in the soil. The conversation here is not about racing, but about patience. How to endure through lean months, how to coordinate leaf out with the gradual release of resources, and how to hold on to reserves for the long winter. Signal noise is one of the most intriguing challenges in tropical forests. With hundreds of species releasing volatile compounds into the air, it becomes difficult to stand out. A tree warning its neighbors of insect attack may inadvertently trigger responses in unrelated species. Some plants may even eavesdrop deliberately, gaining an advantage by listening to signals not intended for them. The sheer density of overlapping scents, hormones, and cues creates a chemical chatterbox of the canopy, where meaning is never entirely private. In temperate forests, Where fewer species dominate, signals are more likely to be relevant to close kin or long-term partners. A beech tree warning of herbivory may be signaling to other beeches nearby, making the communication more direct and effective. The air may carry fewer competing messages, allowing signals to travel farther with less distortion. In this quieter environment, the forest's chemical telegraph is easier to read. Case studies highlight these differences vividly. In tropical ecosystems, fig trees are a keystone species, sustaining countless animals with their nearly year-round fruiting. Their alliances with specialized wasp pollinators are finely tuned, each fig species tied to one or a few wasp species in a partnership that has lasted for tens of millions of years. The chemical cues that figs release to attract their pollinators are precise, drawing in the right wasps even amidst a rainforest thick with competing scents. The reliability of these alliances stabilizes the broader community, anchoring the chaos of diversity with a few dependable bonds. In temperate woodlands, the partnership between beech and fir trees paints a different picture. These species often grow together, sharing fungal networks that transfer carbon, nitrogen, and water. Studies have shown that when one species is stressed, the other can help compensate, lending resources through their shared fungal partners. The relationship is not one of absolute altruism. Flows depend on context and availability, but it reflects a level of neighborly connection made easier in a community with fewer voices. Instead of hundreds of species scrambling to form fleeting partnerships, these trees rely on steady, long-lived associations that endure through generations. The architecture of the two forest types reinforces these contrasts. In tropical forests, towering emergent trees rise above a dense, multi-layered canopy, creating microclimates stacked like stories of a skyscraper. Signals, seeds, and nutrients must traverse vast vertical distances, adding complexity to every exchange. In temperate forests, canopies are often simpler, with fewer vertical layers and clearer lines of communication from root to crown. The flow of information and resources feels less like navigating a bustling metropolis, and more like living in a quiet town where most neighbors are familiar. Yet despite these differences, common themes emerge. Both tropical and temperate forests depend on fungal partnerships to mediate exchanges. Both rely on seasonal or cyclical cues to synchronize flowering, fruiting, or leaf flush. Both balance competition with cooperation, sometimes shading out neighbors, other times supporting seedlings through shared networks. The language differs, the pace varies, but the grammar of survival remains the same. Standing in a tropical forest surrounded by a chorus of bird calls, insect buzz, and the constant drip of water, one feels the energy of a fast-paced, crowded conversation. Signals are everywhere, fleeting, complex, and often noisy. In a temperate forest with its hushed canopy and slower rhythms, the conversation feels deliberate, patient, and steady. Both are beautiful, both essential, and both show how trees have adapted their communication to the environments they inhabit. So the next time you wander into the green shade of a woodland, consider the dialect it is speaking. Is it the rapid-fire chatter of the tropics, where every moment is a race? Or is it the measured conversation of the temperate world, where patience is the virtue that ensures survival? Forests may be silent to our ears, but their languages are rich, and they differ as widely as the climates that shape them. Life for a city tree is very different from life in a forest. Instead of a sprawling root system reaching into rich soil, there may be a cramped pit of compacted dirt surrounded by asphalt. Instead of the cool, buffered climate of a woodland, there is the relentless heat of pavements and walls. Instead of fungal partners in abundance, there may be little more than sterile soil, choked with pollutants and salt from winter roads. Yet city trees persist, holding on in these concrete jungles, communicating in their own constrained way, and shaping not only their own survival, but also the well-being of the people around them. The stresses are constant. Heat islands form when concrete and asphalt absorb sunlight during the day and release it slowly at night, raising urban temperatures several degrees higher than surrounding countryside. For a tree, this means more evaporation, higher demand for water, and greater risk of hydraulic failure. Compaction is another enemy, as the constant weight of vehicles and foot traffic squeezes the soil until roots cannot breathe or spread. Add to this the burden of pollution, nitrogen oxides from cars, particulate matter from industry, and salt from winter road treatment, and the city becomes an environment as harsh as any desert or tidal swamp. Even pruning, though necessary for safety around power lines and buildings, is another wound to heal, another interruption in the natural architecture of growth. Fungal partnerships are far scarcer here than in forests. Mycorrhizae struggle in disturbed, compacted and chemically altered soils. Without them, city trees lose vital allies in nutrient and water acquisition. Some species can survive on their own, but most grow weaker without the hidden threads that would normally stitch them into a supportive network. Each tree becomes more of an island, cut off from the community connections that sustain forests. Roots, too, face peculiar dramas in the city. Confined to narrow pits or containers, they circle endlessly, sometimes strangling themselves. They are hemmed in by pipes, foundations and sidewalks, with little room to explore. When rainfall comes, much of it is whisked away into drains before roots can capture it. In this fragmented underground, communication through shared fungi or overlapping root systems is greatly diminished. The tree must rely more heavily on its own internal stores, turning inward rather than outward. To endure, city trees deploy strategies that prioritize survival over expansion. Hydraulic buffering becomes essential. Trees regulate their stomata carefully, closing early to conserve water even at the cost of photosynthesis. Their hydraulic system acts like a cautious accountant, never risking too much loss at once. Carbohydrate storage is another key tactic. During favorable periods, sugars are stockpiled in roots and trunks, building reserves that can be drawn upon during heat waves, droughts, or heavy pruning. These reserves are the safety net of urban life, compensating for the unpredictability of resources. Species selection also matters. Not all trees are equally suited to city life. Hardy species such as plane trees, lindens, or ginkgos have become staples of urban planting because they can tolerate pollution, restricted rooting space, and regular pruning. Their communication is less about fungal networks and more about resilience built into their physiology. They're chosen not because they mimic the intricate social webs of forest trees, but because they can endure isolation. Yet despite their struggles, city trees also participate in a remarkable human feedback loop. Their signals reach us in ways that go beyond chemistry. Shade cools streets and reduces heat stress for people. The transpiration of leaves adds humidity, lowering temperatures and even reducing energy use in buildings. Greenery filters air, intercepts dust and muffles sound. Perhaps most importantly, trees provide psychological calm. Studies consistently show that time spent near trees reduces stress, improves mood, and even correlates with lower rates of illness. A tree shading a busy street is not only fighting its own battles, but quietly improving the health of everyone who passes beneath it. This loop goes both ways. People care for city trees, watering them in heat waves, mulching their bases, and protecting them with ordinances or community planting programs. Cities that invest in tree care reap returns in cooler neighborhoods, healthier citizens, and more attractive spaces. Neglect, by contrast, leads to decline. Trees struggling in bare pits, bark damaged by vehicles, roots starved of oxygen. Our actions feed back into the survival of the urban forest, just as the trees feed back into our well-being. City trees may not communicate through vast fungal networks or towering canopies, but their presence is still a form of dialogue. They speak to us through shade and scent, through the hush of leaves in traffic noise, through the relief of stepping under a green canopy on a hot day. We in turn respond with maintenance, protection, and sometimes neglect. The relationship is reciprocal, even if we do not always recognize it. So when you pass a lone tree standing in a square of pavement, consider the invisible struggles it faces. Heat radiates from the ground, roots coil against concrete, and fungal partners are scarce. Yet still it sends messages within itself, hydraulic pulses, carbohydrate shifts, hormonal cues, balancing survival in a hostile landscape. And still it gives back, cooling air, cleaning pollution, and offering a quiet moment of calm. In a city that never sleeps, the tree is both survivor and healer, a green companion under concrete skies. The forests of the future will not be quite the forests we know today. Rising temperatures, shifting rainfall, and creeping changes in climate are already altering the conversations trees have with their environment and with one another. The messages are the same: water, carbon, nutrients, defense. But the context is changing, and with it the survival strategies that have served for millennia. To walk through a woodland now is to hear echoes of a dialogue that is being rewritten under new rules of heat and drought. One of the most pressing changes involves the economics of stomata, the tiny pores on leaves that regulate gas exchange. Trees open their stomata to take in carbon dioxide for photosynthesis, but every opening also lets water escape. The balance between carbon gain and water loss has always been delicate, but under rising temperatures the stakes are higher. A measure called vapor pressure deficit, or VPD, captures the dryness of the air. As the atmosphere warms, it can hold more moisture, and it demands more from leaves. A high VPD means water evaporates quickly, pulling harder at every open pore. To cope, trees must tighten control over their stomata. In high VPD conditions, they close sooner, trading photosynthesis for water conservation. This keeps them alive in the short term, but at the cost of growth. Over time, whole forests can slow, their productivity diminish not because sunlight or carbon dioxide is lacking, but because the economics of water make photosynthesis too risky. It is like trying to run a business where every sale costs more than it earns. The books no longer balance. The legacy of drought adds further weight. Trees that endure one severe drought often carry scars for years. Root systems may be damaged, hydraulic pathways embolized, carbohydrate reserves depleted. Even after rains return, recovery can be slow. Growth may remain stunted, defenses weakened, and reproductive output reduced. This drought memory is not the helpful priming kind that sharpens future responses, but a physiological debt that takes years to repay. In some cases, repeated droughts arrive before recovery is complete, pushing trees into decline. Whole forests show these legacies. After severe droughts, dieback can ripple across landscapes, with weakened trees succumbing to pests or failing to regenerate. The structure of the community shifts as some species prove more resilient than others. Oaks may endure where pines falter, or deep-rooted species may thrive while shallow-rooted neighbors dwindle. Over decades, these differences accumulate, reshaping the composition of woodlands. Climate change also forces trees to move, or rather to try. As average temperatures climb, suitable habitats shift northward or upslope. Seeds carried by wind, water, or animals may colonize new areas, while former strongholds become too hot or dry. Rain shifts are not new in evolutionary history, but the pace now is unprecedented. Some species can track the changes, especially those with light, far-traveling seeds. Others, with heavy seeds or specific dispersal partners, may struggle to keep up. As ranges shift, forests are forming new combinations. Trees that have never shared space before now find themselves neighbours. Their fungal partners, insect pests and pollinators, may or may not follow, leading to rewiring of networks underground and in the canopy. Some pairings may be mutually beneficial, creating unexpected resilience. Others may be fraught, with pathogens jumping into naive hosts or competition intensifying where resources are scarce. Forests of the future may look familiar in silhouette but be novel in composition, a blend of old species in new arrangements. Faced with this, humans are experimenting with assisted migration, the deliberate moving of tree species to regions where they are predicted to thrive under future climates. It is a bold step, carrying both promise and risk. Planting drought-tolerant trees in areas likely to dry may preserve forest cover and ecosystem services, but it also risks unforeseen consequences, invasive behavior, disruption of local species, or mismatched partnerships with fungi and pollinators. Assisted migration is a reminder that we are now participants in the conversation, not just observers. Our choices shape which voices remain in the chorus. Amid these challenges, there is room for cautious optimism. Trees are resilient organisms, veterans of ice ages, drought cycles, and volcanic winters. Their strategies are diverse, from deep roots to chemical defenses to long-lived seeds. Forests have rebounded from disturbances before, and many will again. Human stewardship, guided by science, can bolster this resilience, protecting old growth reserves, restoring degraded lands, connecting fragmented habitats, and planting with an eye to future climates rather than past ones. The forest conversations of tomorrow will not be the same as those of yesterday. They will be tuned to higher VPDs, scarred by drought legacies, reshaped by shifting ranges, and rewired by new partnerships. But they will still be conversations, exchanges of signals, nutrients, and life. If we listen carefully, we may find that even as the dialect changes, the essence remains: survival through connection, adaptation through diversity, and the quiet persistence of trees in a changing world. For us, the message is clear. Forests are not passive backdrops to human life, but active participants in Earth's future. Their health is intertwined with ours, their resilience a buffer for our own climate challenges. To care for them is not just to preserve beauty, but to ensure stability, shade, and breath for generations to come. And perhaps, if we act wisely, the forests of the future will continue to whisper their ancient lessons, adapt, endure, and grow, even in the face of new and rising heat. To say that trees talk is one thing, but how do we know? After all, their messages are silent, chemical, and often hidden deep underground or inside tissues. The answers have come from decades of scientific detective work, using tools that can measure flows too small to see, signals too faint to smell, and networks too fine to untangle with the naked eye. To listen to trees, scientists have had to become translators, inventing ways to capture whispers carried in water, sap, and scent. One of the most straightforward ways to eavesdrop is to measure sap flow. Special sensors can be inserted into a trunk, tracking how fast water is moving upward through the xylem. These sap flow sensors often use tiny heaters and thermocouples. By applying a pulse of heat and watching how quickly it moves, researchers can calculate the velocity of water inside the tree. With this, they can tell when a tree is drinking deeply, when it is conserving, and how its daily rhythms of thirst rise and fall with sunlight and temperature. A graph of sap flow is like a pulse chart, a heartbeat of the tree's water economy. Dendrometers offer another perspective. These instruments measure the swelling and shrinking of a tree trunk with exquisite precision, sometimes down to microns. As water status changes, trunks subtly expand or contract, revealing when a tree is hydrated or under stress. Over weeks and months, dendrometers also record growth, capturing the addition of wood with each season. From the outside, a trunk looks solid and still, but with dendrometers it becomes a living gauge of hydration, stress, and progress. Electrical activity is another hidden signal. Just as nerves carry impulses in animals, trees generate action potential like spikes and slower waves in response to damage, heat, or drought. Tiny electrodes attached to bark can detect these faint pulses, charting the movement of signals through stems and leaves. Electrophysiology in plants is not as obvious as a human brain scan, but it allows researchers to follow the faint crackle of messages moving through tissues, illuminating how one part of a tree notifies another of stress. Listening above ground is only half the story. To catch chemical messages released into the air, scientists use VOC traps. These devices capture volatile organic compounds drifting from leaves, such as green leaf volatiles, jasminettes, or terpenes. The trapped chemicals are then analyzed with mass spectrometry, which separates and identifies molecules with astonishing precision. With this, researchers can map exactly what bouquet of scents a tree emits when it is attacked by insects or stressed by drought. The air around a tree becomes legible, full of coded signals invisible to human senses. Isotopic tracers provide another way to follow flows. By giving a tree water or carbon marked with a rare isotope, scientists can track where those atoms go. Labeled carbon dioxide fed to one leaf may later appear in the roots of a neighbor, showing that carbon has moved through a fungal network. Heavy water molecules introduced to the soil can reveal how far and how fast they travel up the xylem. These tracers act like fluorescent dye in a river, making invisible movements suddenly visible, mapping the connections among roots, fungi, and stems. Below ground, mycorrhizal partnerships demand their own set of tools. Soil samples examined under microscopes reveal fungal hyphae, stained and lit to highlight their delicate threads. DNA sequencing has revolutionized this work, allowing researchers to identify which fungi are present without needing to see them directly. By analyzing soil DNA, scientists can piece together which species of fungi are linking which trees, uncovering the complex web of partnerships that make up the forest network. Combined with isotopic tracers, these techniques can show not just who is connected, but what they are sharing. Each of these methods has limits, and careful experiments are required to interpret them. Sap flow sensors, for instance, reveal water movement, but not its ultimate cause. A decline in flow might mean drought stress, root damage, or even pruning of leaves. VOC traps capture chemical messages, but do not tell us exactly how neighboring plants interpret them. Electrophysiology records spikes of activity, but leaves open the question of how those spikes translate into behavior. The challenge is always to move from measurement to meaning, from data to dialogue. This is why experimental design matters so much. Scientists often grow seedlings in controlled chambers, exposing some to stress and leaving others as controls. They may connect plants through shared fungal networks or separate them with barriers to see where the messages travel. By adding isotopic tracers to one and testing others for their presence, they can confirm whether real transfers have occurred. Each layer of complexity requires another layer of evidence, and the picture of tree communication is built piece by piece, with patience and caution. Even in the most careful experiments, inference has boundaries. We can measure signals, track flows, and observe outcomes, but we cannot assume that trees are talking in the way we do. The temptation to anthropomorphize is strong. Forests as societies, trees as wise elders, but the science requires precision. What we call communication may often be side effects of physiology, exploited by neighbors rather than intended for them. Still, the fact remains that messages are moving, and they shape how forests grow and survive. In this sense, listening to trees is both a technical challenge and a philosophical one. Our instruments make the invisible audible, but interpretation demands humility. The signals are real, the flows measurable, but their meaning is written in the grammar of evolution, not intention. The tools of modern science have given us remarkable access to the inner lives of trees. From sap pulses and electrical flickers to scented molecules and fungal DNA, we can now map conversations once hidden in silence. And while the limits of inference remain, each new technique brings us closer to understanding how forests work as communities rather than collections of individuals. So when scientists speak of trees talking, it is not metaphor pulled from thin air, but evidence distilled from sensors, tracers, and microscopes. To listen is to measure, and to measure is to glimpse the secret rhythms of life that unfold too slowly or subtly for us to perceive unaided. The forest may not speak in words, but it leaves signals everywhere, waiting for us to hear them. Dawn begins not with noise, but with light. Before the first bird calls, before the air warms, the faintest glow on the horizon stirs a tree's inner clocks. Photoreceptors in the leaves sense the change, resetting circadian rhythms that have been ticking through the night. Stomata begin to stir, those tiny pores on leaf surfaces preparing to open. As they do, carbon dioxide starts to flow in, meeting sunlight to fuel photosynthesis. Sugars are minted in chloroplasts, the day's currency of energy. Some of these are sent to growing tips, others to roots, and still others are set aside for storage. The tree's bloodstream awakens, phloem filling with sweetness, xylem carrying the first morning rush of water upward. By mid-morning, the sun is stronger and photosynthesis is in full swing. Water races up the trunk, pulled by evaporation from thousands of leaves. Each molecule leaving a stoma tugs the next in line, creating a continuous column stretching from root tip to crown. It is a fragile miracle, always at risk of breaking, but most days it holds. Sugars flow downward as well, powering the roots that dig through soil, the cells that divide at growth points, and the fungi waiting for their share. Around this time, chemical chatter picks up. Leaves may release subtle compounds into the air, warning of a nibbling insect or enticing a pollinator toward a flower. These scents drift invisibly, caught on breezes, intercepted by neighbors, folded into the day's background of signals. By midday, the strain is greatest. Sunlight is fierce, temperatures high, and vapor pressure deficit pulls water faster than roots can always supply. Stomata weigh their options, remain open to maximize photosynthesis, or close partially to conserve water. Some do one, some the other, balancing risk and gain. Deep inside, xylem vessels are under tension, some cavitating into tiny bubbles that break the flow. Around wounds or bites, electrical pulses ripple through tissues like a faint whisper of quiet lightning. Defense chemicals surge, tannins stiffen, and enzymes prepare toxins to ward off further attack. To us the tree looks still, but inside it is buzzing with activity, a midday dance of growth, defense, and restraint. In the afternoon, the balance eases, temperatures begin to fall, and water columns stabilize. Photosynthesis continues, but with less strain. Sugars accumulate, and the phloem network begins its evening duty of transport. Energy is distributed to roots, where it fuels both growth and trade with fungi. Mycorrhizal partners extend the tree's reach into the soil, absorbing phosphorus and nitrogen in exchange for carbon. This underground economy peaks as the day wanes, with trees shuttling the products of sunlight to their fungal allies, and fungi paying back with minerals gathered from the soil maze. Evening brings a subtle shift. As the light fades, stomata begin to close, conserving water for the night. Photosynthesis slows, then ceases, but the work is not over. Sugars continue to move, fueling repair and replenishment. Damage from midday heat and herbivores is patched. Proteins are rebuilt, and DNA is checked and maintained. Trees may not sleep as animals do, but they do rest, shifting priorities from capture to maintenance. Leaves, stems, and roots each perform their nightly duties, guided by circadian rhythms tuned to the cycle of the sun. Night in the forest is a time of hidden negotiation. With stomata closed, respiration dominates, releasing carbon dioxide back into the air. Roots exhale, soil microbes stir, and the forest breathes in a different rhythm. Underground, fungal trade continues. Carbon flows outward into hyphae, exchanged for minerals and water. In return, messages travel back, traces of stress in the soil, hints of neighbours, signals that prime defences for the day ahead. The night is quieter, but it is not still. It is the time for calibration, when reserves are balanced, debts settled, and tissues primed for the next dawn. Even in darkness there is communication. Some trees release nighttime volatiles, subtle scents that deter herbivores or attract nocturnal allies. Roots exude compounds into the soil, shaping microbial communities, encouraging some, discouraging others. Fungi redistribute nutrients, sometimes linking multiple trees, sometimes rerouting carbon from one partner to another. These exchanges are not visible, but they define the structure of the forest. Each tree is not just an individual, but a node in a network, carrying on negotiations in the hush of night. By the time the stars fade and the first light brushes the canopy again, the cycle is ready to begin anew. Stomata will open, water will rise, and sugars will flow. The tree's day is not a single act, but a rhythm, repeated thousands of times across a lifespan that may span centuries. Each cycle is familiar, yet each carries its own variations. Heat waves, storms, insect outbreaks, droughts, and the gentle days in between. The quiet story of a tree is told not in dramatic gestures, but in steady routines, endlessly repeated, endlessly adjusted. To us, a tree's life seems slow, almost immobile, yet within each day is a symphony of signals, decisions, and exchanges. Dawn brings the promise of sunlight, midday tests endurance, evening distributes rewards, and night consolidates the gains. Together these cycles weave the life of the forest, integrating light, water, air, and soil into a seamless flow. It is a rhythm so steady we overlook it, but once noticed, it reveals the tree not as silent, but as deeply alive, conversing with its world in the language of cycles. A forest to the human ear is quiet. You may hear birdsong, the rustle of leaves, the creak of trunks in the wind, but the trees themselves seem mute. And yet, as we have followed their signals through sap and scent, through fungal threads and chemical marks, a different picture emerges. The stillness is only on the surface. Beneath bark and soil, in crowns and roots, trees are engaged in a continuous slow conversation, one that mixes whispers of stress, murmurs of exchange, and the faint hum of life balancing itself day by day. The messages take many forms. Electrical flickers ripple through tissues, spreading word of a cut or a burn. Hydraulic pulses relay the state of thirst or abundance, shaping when stomata open and close. Chemical scents drift into the air, warning neighbours of insects or attracting allies to devour them. Underground, fungal threads ferry not only phosphorus and nitrogen, but also signals of distress and opportunity, binding trees into networks that are both markets and messengers. Each mode of communication is partial, imperfect, and often unintended, but together they form a tapestry that sustains the forest. These exchanges remind us that forests are neither harmonious utopias nor ruthless arenas. They are mosaics of cooperation and competition, shifting with the seasons and the years. A parent tree may ease the path of its offspring with carbon subsidies, while at the same time casting dense shade that tests their endurance. A fungal partner may enrich a tree with nutrients, yet siphon carbon from a neighbor struggling in drought. A walnut may release toxins to thin the crowd, while a birch may lend sugars to a shaded fir. The forest is a stage where strategies overlap, sometimes generous, sometimes harsh, always pragmatic. Time deepens this complexity. On a human scale, we notice the fall of a single tree, the opening of a sunny gap, the flowering of a woodland in spring. But trees measure in decades and centuries. Their conversations unfold at speeds so slow they escape casual notice. An oak scarred by drought may carry that memory for years, shaping its stomatal caution long after the skies have cleared. A spruce in the boreal zone adjusts to freeze and thaw year after year, its hydraulic system retrained by repetition. Fungal partnerships rewire themselves as soils shift and species come and go. What we see as static is, in fact, a dialogue in deep time. This slowness does not mean silence. It means that the hum of life in a forest is tuned to a tempo different from ours. The intervals are measured in seasons rather than minutes, in centuries rather than years. When a tree responds to its neighbor's warning scent, when roots shift to avoid kin or confront strangers, when networks redirect nutrients from one partner to another, these are not accidents, but elements of a steady conversation. Slowness is simply another form of speed, one suited to lives that outlast generations of human history. There is also humility in recognizing the limits of what we can know. Our instruments capture sap flow, trace isotopes, detect faint electrical spikes, and sequence fungal DNA. These tools let us glimpse the hidden dialogues of trees, but interpretation is always careful work. We must resist the temptation to project our own forms of language or intention onto forests. The messages are not words or thoughts, but physiological signals honed by evolution. They are communication in the broadest sense, information passed, received, and acted upon, regardless of intent. That in itself is extraordinary. The lesson for us then is twofold. First, forests are not inert backdrops but living communities. Their resilience depends on connections as much as on individuals. Each fallen trunk, each fungal thread, each chemical puff of scent is part of a system that persists because of its interwoven nature. Second, we are part of these systems, whether we acknowledge it or not. Our actions alter the rhythms, sometimes snapping networks, sometimes fostering recovery. To recognize the quiet talk of trees is to understand that silence is never emptiness. It is full of life working at a slower beat. As we gather the threads of these forest conversations, a final image lingers. Night has fallen, and the wind drifts softly through the crowns. Stomata are closed, photosynthesis has ceased, but the work continues. Sugars are moving, roots are exhaling, fungi are redistributing nutrients, and faint chemical traces seep into the soil. The forest is at rest, but never idle. It hums beneath our feet, a network breathing, remembering, and preparing for the dawn. Slowness is not silence. A forest may appear still, but life inside it is in constant motion, exchanging signals, negotiating survival, and building connections that stretch across generations. To listen to trees is not to expect voices, but to tune our senses to the subtler scales of life. And when we do, we find that the world around us is speaking all the time, in pulses, in scents, in threads, reminding us that communication is as old as life itself, and as enduring as the night wind moving gently through the crowns.